Learn all about fine-tuning LLM models. In this course, Chris will teach you fine-tuning using QLORA and LORA, as well as quantization using Llama 2, Gradient, and the Google Gemma model. This crash course includes both theoretical and practical instruction to help you understand how to perform fine-tuning.
So guys, here is an amazing crash course to help you understand that how actually you can perform fine-tuning. Specifically with respect to LLM models. And again, in this crash course, we will be discussing the theoretical intuition, what exactly fine-tuning is, how you can actually perform fine-tuning. We'll be learning about concepts such as quantization, LoRa, QLORA, PEFT, right? And along with that, we will be implementing multiple projects with the help of Hugging Face, open source LLM models like Llama 2. Along with that, we'll also be seeing how you can perform fine-tuning with your own custom data set with the help of Google Gemma model. Now, in most of the companies that are probably looking for generative AI roles, usually want this specific skill set of fine-tuning, and you should definitely know how you can actually fine-tune with your own custom data set and how you can solve different use cases. So this entire crash course will be having a step-by-step process of understanding. It includes both theoretical intuition, practical intuition, and we will be also developing completely end-to-end solutions with respect to this. So I hope you will enjoy this series. Please make sure that you watch this series till the end, and definitely you will be able to learn a lot of things out of it. So yes, best of luck. Let's go ahead and watch this series. In one of our previous video, I'd already shown you how you can actually fine-tune Llama 2 model with your own custom data set. And over there, we learned about, or we saw code that were related to something called as quantization, LoRa, QLORA techniques and all, right? And all these techniques are super important if you also want to train or fine tune your own LLM models with your own custom data set. Now, when I showed the code, right, when I executed that particular code, many people had actually requested to explain the theoretical in-depth intuition about it. And that is what I'm actually going to do. The best thing is that when I learned about this theoretical intuition, and I'm doing it from past 2 to 3 months, it's quite amazing, guys. Now this is where that machine learning era is probably coming, where I used to upload a lot of theoretical in-depth geometrical intuitions regarding various machine learning algorithms. Similarly, here also in this series of videos, in this video, we are going to discuss about quantization. Now, what exactly is quantization? We are going to discuss about that. In the upcoming video, we are going to see techniques like LoRa, QLORA, every maths intuition that is probably involved. And this all are important for the fine-tuning technique, right? If I probably talk about generative AI, one of the most important interview questions will be something related to fine-tuning and what is the techniques that is usually used behind it, right? So what all things we are going to cover in this video? In this video, we are going to talk about quantization. Specifically, when I say quantization, it is all about model quantization, because if you remember in our Llama 2 code, right, when we are doing the fine tuning, here you could see that we had put some parameters, right, regarding precision based modeling. We had spoken about quantization, when we are downloading the models, from a higher bit to a lower bit. Why we are specifically doing this, I will be explaining about that, right? So with respect to each and every parameters, definitely I will explain you the theoretical intuition, and later on you just go ahead and see my previous video with respect to all the coding. Now everything will make sense. Okay, so what exactly is quantization? We're going to discuss. We're going to discuss about full precision, half precision, and this is something related to data types, like how the data is stored in the memory. When I specifically say data in LLM models, I will talk about weights and parameters, right? Because at the end of the day, LLMs are also deep learning neural networks in the form of transformers or BERT, right? Then we're going to discuss what exactly is calibration. This is also called as like calibration in model quantization, right? We are going to also make sure that we are going to see some problems, right? How we can actually do calibration. Then there is different modes of quantization, right? First of all, I will explain you the definition, then only you'll be able to understand. In modes of quantization, we are going to discuss about 2 types. One is post-training quantization and quantization-aware training, right? So these all are very important in terms of fine-tuning techniques. Now, let's go ahead and talk about quantization, and we will try to see the definition, right? Quantization, okay? Now, if you want to really understand the meaning of quantization, it is better to write a simple definition for it. Okay. So quantization basically means conversion from higher memory format to a lower memory format, right? Now, I've written a very generic definition what exactly quantization mean. It is nothing but conversion from a higher memory format to a lower memory format. Now, when I say higher memory format, let's consider any data, right? And if I probably consider any neural network, okay? So let's say if I have neural network, right? And when we train this neural network, right? All these neural network are interconnected. At the end of the day, what are the parameters that is probably involved over here? It is nothing but weights, right? We specifically have weights. Now, weights are usually in the form of metrics, right? Let's say that I have a 3x3 weight. Okay, I'm just taking as an example. In one of the layer, I have 3x3 weights. And over here, every value, right, is probably stored in the memory in the form of 32 bits, right? 32 bits. We also say this bits as, we also denote it as something like FP32. Now, what exactly is FP32? So FP32 basically means I can also consider it as, see, FP full form is not floating point, okay? But I'm just writing floating point 32 bits, right? When I say FP basically means it is nothing but full precision, right? Full precision or single precision. Okay, so this is the definition that is probably given, right? But in short, this is like a floating point number, okay? So over here, let's say my number is somewhere around 7.23. Now, this number is stored based on 32 bits in the memory, right? Now, understand when you have a very big neural network or you have LLM models, right? As you see different LLM models, right? Parameters keeps on increasing, right? Some may have 70 billion parameters. If I probably consider Llama 2 with 70 billion parameters, that basically means it has 70 billion parameters in terms of weights and bias. Okay. Now it is not possible for me to, let's say I want to use this particular model and I want to probably do some fine tuning with respect to the normal GPU that I have, right? And let's say I have a very limited RAM in my system. Let's say the RAM I have is somewhere around 32 GB, right? I cannot directly download this specific model and put it in my RAM itself, right? Let's say, or load it in my VRAM that is available in the GPU, because GPU also has some limited RAM, right? And it is not possible. You cannot directly download it. Obviously, it will require huge space. The other way is that, yes, I can probably take a cloud space somewhere. Let's say in AWS, I can create my instance. I can say, hey, give me this much RAM, 64 GB RAM, and I probably want this much GPU. And then I will try to load the model over there. That you can do it. But over there, what is basically happening? Lot of cost is involved, right? Based on the resources. The cost is involved, right? So in this scenario, and why this 70 billion parameter is happening? Why this model has a 70 billion parameter? Because every weights or every bias that is available in this, this may be getting stored in 32 bits. So what we can specifically do is that we can convert this 32 bits into, as I said over here, see, conversion from a higher memory format to a lower memory format. Let's say I can probably convert this 32 bit into int 8 and then download the model or then use the model, right? After doing this, what will happen? Within my system, I will be able to inference it, right? Obviously, for fine tuning, if I want to fine tune it with a new data set, I will obviously require GPU. But if I consider with respect to inferencing, it becomes quite easy, because now all my values that are stored in the form of 32 bits, it will be stored in the form of 8 bits. So what we are specifically doing over here, we are converting from a high memory format to a low memory format, and this is what is called as quantization. A very important thing. Now, why quantization is important? Because you will be able to inference it quickly. See, inferencing basically means what? If I have an LLM model, if I give any input to that, I should be able to get any output, right? I should be able to get response, right? Now, when I give any input, all the calculation with respect to different weights will happen, right? And obviously, if I have a bigger GPU, this inferencing will quickly happen, right? But if I have a GPU with less cores, let's say, then what will happen? This calculation will take time. But if I convert my 32-bit to 8 bits, right? Every weights are basically converted into 8 bits. Now, just imagine the calculation. Will there be a difference? Yes, it will happen a little bit much more quicker. So, quantization is very much important for inferencing. And some of the examples that I again probably talk about is that, and obviously you may have heard about this. It's not like only in LLM models we specifically do, right? In different computer vision models, in NLP models also, where you think that there is a lot of weights that is involved, and all these weights, if I want to quantize it, right, I can actually do it, right? Now this inferencing, let's say I want to use a specific deep learning model in my mobile phone. So in my mobile phone, if I want to use it, right, in a specific app, then what I will do? I will try to quantize, right, whatever deep learning model I have created from 32 bits to 8 bit, and then I will try to deploy it in my mobile phone or any edge device, right? It is not possible that you can probably deploy this big model over there, right? It is not possible with so and so many parameters. So what we do? We basically perform quantization. So I hope you are able to understand over here. Quantization is nothing but we are trying to lower down the memory, right, with respect to any weights that we have, like from 32 to probably int 8, or let's say FP16. We can also say FP16, right? Let's say if I have an FP32 bit that is specifically required to store any information in my memory, I can also convert this into FP16 bit. This is also quantization only, right? Usually all these values are stored in floating point, right? We specifically say this FP32 bit, we say single precision or full precision. We for FP16 bit, if I'm trying to convert like this, it is basically called as half precision, right? So you should be able to understand all these technical terms, right? And in short, these are nothing but these are floating point numbers, right? Now similarly, in TensorFlow also you'll be able to see. When we probably work with TensorFlow, you'll find TF32 bit, right? The data types, the numbers are stored in this particular format, right? And it is important, okay? This is all our terminologies that are super important. But I hope you got an idea. What is the main aim? What is the main motivation out of quantization is that if I have a bigger model, I should be able to quantize it and make it as a smaller model so that I can use it for my faster inferencing purpose, both in mobile phones, in the edge devices, let's say in even watches, smart watches, I want to use it over here. I can actually do that, right? Now, if I talk with respect to LLM model also, with the help of quantization, see, once we compress this particular model, right, later on, we can also perform fine tuning, right? Fine tuning. But here, there is one disadvantage. When we quantize, right, when we perform this quantization, since we are converting from 32 bits to int 8, let's say as an example, there is some loss of information also. And because of this, there will be some loss of accuracy. Now, how to overcome this? We will talk about it. There are different techniques how we can specifically overcome it. But I hope you got an example. What exactly is quantization? What is full precision, half precision? Half precision example is something like this. Now, let's talk about what exactly is calibration. Now, calibration basically means how we will be able to convert this 32 bit into int 8. Like, what is the formula? What is the mathematical intuition that is specifically required? Let's go ahead and discuss that. So guys, now let's go ahead and try to understand how to perform quantization. And this is super important in terms of mathematical concept that I'm probably going to talk about. Because with the help of TensorFlow, just by writing 4 lines of code, I will be able to perform quantization. But it is important, you should know that how you can actually do it manually. Whenever I talk in terms of what are the types of quantization that we have. So we have 2 different types of quantization. One is symmetric quantization and one is called as asymmetric quantization. Now, just by showing you an example, you will be able to understand what is the exact difference between them. Okay. Let's say I have a task, and this first task that I am probably going to talk is with respect to symmetric. And understand, I hope in deep learning you have heard of something called as batch normalization. So if you have heard about this batch normalization, so batch normalization is a technique of symmetric quantization, right? So every time you'll be able to see that whenever we do forward propagation and backward propagation, in between all the layers, we apply batch normalization so that all our weights are zero centered. That is near the zero, and the entire distribution of the weights will be centered near zero. Okay. So batch normalization is one technique of symmetric quantization. So let's go ahead and see one example. So this will be my first example over here. I will go ahead and write it down. And now you'll be able to understand it, how symmetric quantization is basically performed. And what is symmetric quantization? You have understood. From higher memory format to lower memory format, we'll try to convert. Okay. So here we are trying to understand the mathematical intuition. So let's go ahead and talk about one technique which is called as symmetric unsigned int 8. Okay. Quantization. So we will see this technique first. Now here, what is our main aim? Let's say I have a floating point number. Okay. So let's go ahead and write it down. Let's say I have a floating point number between 0 to 1000. Or just imagine that these are my weights, right? Whatever matrix weights I have, my values ranges between 0 to 1000. Let's consider in this particular way, right? And this is, let's say, these are the weights for my larger model. Okay, larger model. Okay. Now, one very important thing that you really need to understand, right? When I talk about any larger model, let's consider any LLM model. Okay. So in LLM model, you have a lot of parameters. Let's consider this is one kind of LLM model. Now, when I say all these weights are there, this may be getting stored in 32 bits. Okay. Usually what will happen, guys, the weights will not be in this range also. Okay. It will be in the minimalistic range. So I will just consider this as some numbers. Okay. So that you don't get confused with respect to these are some numbers. I will also not consider LLM model over here. And let's say this numbers are stored in the form of 32 bits. Okay. Now my main aim is to convert this into unsigned int 8. That basically means 8-bit, right? So 8-bit basically means what? 2 raised to 8 is how much? 2 raised to 8. But when we say unsigned, that basically means my value will be ranging between 0 to 255. So I want to quantize from this values to this value. Okay. What is my aim? I want to quantize my range of values between 0 to 1000 to 0 to 255. Okay. This is what is my aim with respect to this. Okay. So this is what is my target. Now let's see. Okay. So if I probably draw just a real points, and the same thing we will do with the weights over there, whatever quantization process we are specifically doing. Let's say I have values between 0 and this is basically 1000. Okay. Then what I will do over here, I want to convert this into again 0 to 255. Okay. Now let me talk about one very important thing, guys. Whenever we have any, let's consider this one. If we have this single precision floating point 32, right? If we have this number, how this number is stored, do you know that? The 1 bit will specifically be used for sign or unsigned values, right? So let's say positive or negative. If positive is there, then this will be +1. If negative is there, it will be -1. So all the values are basically saved between 0 to 1, right? It can be 0 or 1. Okay. Then the next 8 bits are stored for exponent. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is for sign. This all numbers that you see, it is basically stored for exponent. This is how it is stored inside the memory. And remaining 23 numbers, all these 23 bits will basically be saved for Mantissa. This is specifically for the fraction. So if I have a number which looks like 7.32. Now 7.32 is a number, it is a positive number. So for my sign bit, there will be a positive value, let's say 1 over here. Then this 7 will be probably put up in this 8 bit, and remaining 0.32 will be put up in this mantissa, right? So this is how the numbers are basically stored in the memory, right? If I consider an example with respect to FP16, right, half precision floating point 16 bit, then you will be able to see there will be 1 bit for the sign number, there will be 5 bits for the exponent. We basically say exponent 1, 2, 3, 4, 5. Let's consider this 5. Let's draw till here. Okay, so this let's say that this is 5. 1, 2, 3, 4, 5. Okay, so this will be 5, and remaining 10 bits will be saved with respect to mantissa. So we basically say this as a fraction, right? Anything that comes after the decimal, right? And this is how you will be able to see it will take, this will take less memory, this will take high memory, right? Now what is our main aim over here? I already have a 32-bit number. I need to probably convert this into a range of unsigned int 8. Unsigned int 8 basically means I will not take any negative numbers. It will be between 0 to 255, right? This is what I really want to do, okay? Now for this, what will be the equation? And I hope you have heard about something called as min-max scalar. I've repeated so many times this in my machine learning sections also. So any number that is over here, how will I be able to convert from this floating point to this unit int 8, right? Unsigned int 8, right? How I will be able to do it. Now for this, let's go ahead and calculate it and what equation is specifically required, okay? So that basically means over here what we are going to do. 0.0 will be converted into a quantized value of 0, okay? Not 0.0, it will be 0. And similarly, 1000 should be converted to a quantized value of 255. At the end of the day, the bits are decreasing. So quantization is basically happening. But we have to probably come up with a scale factor. Now, what exactly is a scale factor? So let me define a scale over here. So here, the scale formula will be x max divided by x mean. And then they will be divided by q max minus q mean. This q is nothing but quantization. Now, what is the x max over here? 1000, right? So this I will consider as my x. This I will consider as my q, right? I'm showing you how quantization happens in a symmetric distribution. Symmetric basically means all the data is evenly distributed, okay? And we really need to convert this based on this itself. These are evenly distributed. Now, what is x max? X max is nothing but 1000 minus 0. Then q max basically means 255 minus 0, right? So if I probably go ahead with this specific division, right, then what will be the value that I will be having, right? 1000 divided by 255, it is nothing but 3.92. So this is nothing but this is called as a scale factor, right? Scale factor. So any number that I have over here, if I want to convert from this FP32 bit to uint 8, I just need to use the scale along with one formula which is called as round, okay? So I will apply round with respect to any number. Let's say if I consider 500 divided by 3.92, or let's just consider 250 divided by 3.92. So if I want to see what will happen to 250, right? What will be the number in this uint 8? So I can probably go ahead and divide it. It will be nothing but 250 divided by 3.92. So if I go and calculate it, it is nothing but 63.77. So if I do the rounding, that basically means this will be 64. So in short, any number that is over here, let's say it is 250 over here, this will get converted to a quantized value to 64, right? So the same thing the code will also be doing. And this is for symmetric unsigned int 8, okay? Quantization. If I want a quantization for some other factor, let's talk about this, okay? So let's say I have another kind of distribution, and this is time that it is asymmetric. and I want this as u int 8. So if I want to perform this quantization, so what will happen now in this particular case? Let's say if I have a values between minus 20.0 to 1000. Okay. So these are my floating point. Now I want to perform quantization and convert this into 0 to 255. Right. Now in case of asymmetric, what will happen is that in my real number section, right, these numbers are not symmetrically distributed. It may be right skewed, it may be left skewed. Okay. So in this scenario, you will be able to see that my values are ranging between minus 20 to 1000. I want to convert this into this. Now in this scenario, if I apply the same formula, x max minus x mean, so how it will be? 1000 minus 20. So minus of minus 20 is nothing plus 20 divided by 255. So if I probably do the calculation, then you will be able to see that I will be getting somewhere around 4.0. Okay. Now, very important thing, that basically means this 20.0, if I quantize it, right? If I quantize it, it will get converted to something like 4.0. Oh, sorry. This is my scale factor. Okay, scale factor. Now, if I take any number and try to convert it, let's consider minus 20. If I try to convert it by dividing by 4.0, right? And if I do the round, so what it will become? Minus 5, right? Minus 5 of round, this much I will probably get, minus 5, right? Now you can understand that this minus 20.0 is getting converted to minus 5.0. But you can see over here, my distribution starts from 0 to 255. So how can I forcefully make this minus 20.0 to 0? All you have to do is that go ahead and add the same number in a positive way. So in this case, the number that you see, this 5, right? This is basically called as 0 point, right? So there are two important parameters that we specifically talk with respect to quantization. One is 0 point. For the above one, since we have a symmetrical distribution, here the 0 point was 0 only. And the scale was 3.92. In this particular case, since it is asymmetrical distribution, here we have a 0 point as nothing but 5. But scale is 4.0. So these two parameters we usually require to perform quantization. Okay. And these are some of the examples that I have shown you to just give you an idea like how quantization basically happens. And super important in terms of understanding is the simple equations, you'll be able to understand how things are basically working, right? At the end of the day, understand quantization is a simple process of converting that high full single precision or full precision floating point 32 bits into small bits. You know, it can be unsigned integer 8, it can be signed integer 8. If we say signed integer 8, then what will happen? It is that it will be ranging between minus 128 to 127. And based on that, you can specifically apply the formula, right? Now let's go ahead. See, we had already discussed about these two topics. One is this, and second one we wanted to discuss about calibration. Now this squeezing that you could see, right, from here to here to here, here to here, we are squeezing it, right? This squeezing process is basically called as calibration. Whatever process we are basically applying in this quantization process, it is nothing but it is called as calibration, because we are squeezing those values from a higher format to a lower format. Okay. So that is nothing but calibration. So we have completed both this thing. Okay. Now let's see what are the different modes of quantization. One is called as post-training quantization and quantization-aware training, right? I will talk about this, why it is super important, both this technique. Okay. So you'll get an idea about it over here. So first of all, we will go ahead and say post-training quantization. So what exactly is post-training quantization? Here we already have a pre-trained model. So we already have a pre-trained model. Now, if I want to use this pre-trained model, obviously the weights are very high. Here we apply calibration, right? When I say calibration, that basically means squeezing the value from high format to a lower format, right? And then after performing this particular calibration, we take what kind of data? We take that weights data, whatever weights data is basically there in this particular pre-trained model. And then we convert this into a quantized model. Okay. So once we apply this process, then only we will be able to get the quantized model. And then we can use this entire model for any use cases. Okay. For any use cases. Right. This is a simple mechanism with respect to post-training quantization. See, understand, post-training basically means I already have a pre-trained model where my weights are fixed. I don't need to change those weights. I will just take or download those weights. I will take this weights data, apply the calibration, and then convert this into a quantized model, right? The second technique that we have written over here is quantization aware training. Okay, quantization aware training. So let's talk about this. Quantization aware training. This is also called as this is also called as QAT. Okay, so we can write it as QAT. Okay, quantization aware technique. This is basically called as PTQ. Okay. So over here, what is the exact difference we'll try to see between these two. Okay. Now in quantization aware training, what happens? See, over here, what is the problem? If I probably perform calibration and if I create a quantized model, there is a loss of data. And because of this, what will happen is that the accuracy will also decrease. Okay, for any use cases. But in the case of quantization aware training, okay, you will be able to see that we will be taking out trained model, whatever trained model is there. Trained model is there. Okay, let me just go ahead and write it down. Trained model is there. Then we perform quantization. Again, quantization is what? Same, the calibration process will apply over there. We will probably do all these things. Okay. And then once we do this, the next step is that we will go ahead and perform fine tuning. See, we know that with the help of PTQ, you'll be seeing over here on the top, some loss of data and accuracy is there. But here, with respect to fine tuning, we will take new training data. New training data. Now, once we specifically take new training data, we will be fine tuning this model and then we create a quantized model. Quantized model. So with respect to any fine tuning technique that we will be seeing, we don't use post training quantization. We specifically use quantization aware training technique. So that basically means we are just not losing accuracy or data over here because we are in turn adding more data for the training purpose. And through this, we will be fine tuning our data and then we create our quantized models, right? So this is the basic difference. So all the fine tuning technique that I will probably show you in the future will be of this type, that is quantization aware training, so that we do not lose much data accuracy. So I hope you got an idea with respect to all these three techniques, guys. Going ahead, there are two important techniques that we really need to understand. One is QLORA and one is LORA. So these techniques specifically will be also understanding with respect to fine tuning. We are into the part 2 of fine tuning series, and in this particular video, we are going to discuss about LORA and QLORA in-depth intuition. Already in the playlist of fine tuning, I've discussed about quantization, and I hope you have seen the video early. Many people were requesting for LORA and QLORA also. So let's discuss and we will try to discuss the complete in-depth maths intuition. The best thing will be that, guys, I'll try to explain this maths in-depth intuition. I've already seen the research paper, and there are a lot of complicated things that is probably there in the research paper. But I will try to teach you in such a way that at least you should be able to understand, what exactly is LORA, what exactly is QLORA, and then we'll also see one example, how with the help of code you will be able to do it. And trust me, these are some of the very important things in fine tuning, because tomorrow you go in any interviews, you are going to get asked respect to this kind of questions that may be coming, because at the end of the day, any generative AI projects, specifically with LLM, right? LLM models, if you are working in the company, they will be giving you fine tuning task. So let me quickly share my screen and show it to you. So here already I have uploaded a video, part 1, where we have discussed about quantization. A good 32 minutes video, everything you'll be able to understand it, because here I've also used all the mathematical intuitions, everything as possible, as much as possible. To talk about the research paper, so what does LORA means? LORA basically means low rank adaptation of large language models. This is this amazing research paper, and probably you'll be seeing a lot of this kind of equations as you go ahead. There'll be different performance metrics, but as usual, I will do what I'm good at. I will try to break down all these things and probably explain you with respect to examples, with respect to code, and many more things. So quickly, let's go ahead. So why LORA and QLORA is basically used? LORA basically means low rank adaptation, lower order rank adaptation. It is specifically used in fine tuning of LLM models. Okay. So let's go ahead and discuss this, and I've created this amazing diagram over here. Initially, whenever you have a pre-trained LLM model, that basically means, let's say that there is a model, something like GPT-4 or GPT-4 Turbo, right? And this model has been created by OpenAI. So we basically say this model as the base model, okay? GPT-4 Turbo. And this model is trained with huge amount of data, right? So the data sources will be internet, it can be books, it can be multiple sources, right? At the end of the day, all these models, how you can measure them? They may be saying that, hey, it supports 1.5 million tokens, it has been trained with this many number of words, right? So many tokens of words. Now what will happen is that all these models, probably to predict the next word, it will have the context of all those tokens, and then it will be able to give you the response. So these all models are basically base model, and we also say this as a pre-trained model, okay? Some of the examples, again, I'll be telling you GPT-4, GPT-4 Turbo, right? GPT-3, GPT 3.5, something. So all these models are specifically pre-trained models. Now, further, we can take this model, and there are various ways of fine-tuning it. Please make sure that you watch this video till the end. If you watch this video, you will understand everything that is actually required with respect to fine-tuning. And there are multiple ways of fine-tuning also. Now, let's say that I take this model, I do some amount of fine-tuning, okay? And this fine-tuning is done on all the weights of this specific model, right? So, some of the application that we may generate is like ChatGPT, we may generate like cloudy ChatGPT, right? Cloudy GPT itself, like the chatbot that we specifically use. Some of the examples. Okay, so this one way of fine tuning is there, where we train all our parameters. So here we specifically say full parameter training. Okay, so here you can see full parameter fine tuning. So here I'm going to write full parameter fine tuning. Now this is one way of fine tuning, where we train our entire parameter based on our data that we have. Okay, and after training it, we can develop applications like ChatGPT or any custom GPT that you specifically create. As we go ahead, you can also take these models and perform domain specific fine tuning. Okay, so one type of fine tuning is this. The other fine tuning technique that you can specifically use is called as domain specific fine tuning. Some of the example, let's say that I'm fine tuning a chatbot model, which will be for finance. It can be for sales. It can be for different domains itself, right? So here the main important word is domain. So this fine tuning also we can perform. Okay. So again, why I'm saying all these things? Because there are various ways of fine tuning things, right? One more fine tuning we can basically divide by is something called as specific task fine tuning. Now, in case of specific task fine tuning, these are my different tasks. Let's say this is task A, B, C, D. This task can be something related to Q&A chatbot. This task can be something related to document Q&A chatbot, different applications. So that is the reason why we are specifically saying over here as specific task. Okay, specific task fine tuning. Now, perfect. Now, this is good. You have seen all the different ways of fine tuning. Okay. Now let's talk about full parameter fine tuning. Again, I'll repeat it. This is my base model right now. If you use it as an example, as I said, GPT-4 Turbo, GPT 3.5, Gemini 1.4, different models can be there. We can take this base model, we can fine tune and create applications like ChatGPT. We can create other applications like Stable Diffusions, not specifically to LLM, but LLM, we can actually do it. Then we can also further fine tune this based on domain specific fine tuning, right? Based on different domains like finance, sales, retail. We can also take this model and do more specific task fine tuning like task A, task B, task D. Let's say I want to convert this into text to SQL. I want to have this as document Q&A. So I can further fine tune it based on specific task. Now let's talk about this full parameter fine tuning. Okay. And what are the challenges with full parameter fine tuning? And that is where, see, I'm building up the story. Later on, I'll be explaining you where LoRa will be used. Now, in full parameter fine tuning, the major challenge is that we really need to update all the model weights. Let's say that I have a model which has somewhere around 175 billion parameters. That basically means 175 billion weights. Now, in this particular case, whenever I fine tune this model, I need to update all the weights. Great. Now, when I'm saying updating all the model weights, and when we talk about this many number of parameters, why it can be a challenge? Because there will be hardware resource constraint, right? So with respect to different tasks, if I really want to use this particular model, that much RAM I really require for inferencing purpose, that much GPU I really require, right? So for downstream task, it becomes very difficult. Now, what is downstream task? Downstream task, some of the example is like model monitoring, right? Model monitoring. The other task can be like model inferencing, right? Model inferencing. Similarly, the GPU constraint that we may have, the RAM constraint that we may have. So we may face multiple challenges when we have this full parameter tuning, full parameter fine tuning. Now, in order to overcome this challenge, we will specifically use LoRa and QLORA. Okay. What exactly is LoRa? As I said, low order rank adaptation, and QLORA is something, it is also called as LoRa 2.0. So we'll discuss about both of them with respect to mathematical intuition, and you'll get a complete idea what I'm actually trying to say. Now, what does LoRa do? Okay. Now let's read the first point, and this is very much important because in the research paper you will find this equation. Okay, this equation. Now, what exactly LoRa will do? LoRa says that instead of updating all the weights in full parameter fine tuning, right? Instead of updating all the weights, it will not update them. Instead, it will track the changes. It will track the changes. Now, what changes this is basically tracking? It will track the changes of the new weights based on fine tuning. Okay, this is very much important to understand. So, based on the new weights, how we are going to combine these weights with the pre-trained weights. Okay, so here you can see these are my pre-trained weights from the base model. Like let's say that this model is Llama 2. Now, if you're performing fine tuning using LoRa, then LoRa will track the new weights over here, which will be of the same size. Okay, so let's say that if this weight is 3 cross 3, then the new weights, when it is probably doing the forward and the backward propagation, those new weights will be tracked in a separate matrix. And then these two weights will be combined, wherein we will get the fine-tuned weights. Now, this way, what will happen is that this tracking will happen in a separate way. But still, you may be thinking, Krish, here also we are updating all the weights itself, right? So here also the resource constraint will definitely happen. Yeah, fine. I'm talking about 3 cross 3. But what about weights and parameters where there are 175 billion, right? 175 billion parameters or 7 billion parameters. That time I'll be having a huge matrix, right? So at that scenario, you need to now understand how LoRa works. Because this weights, how it is getting tracked, it will just not get tracked in this 3x3 matrix. Instead, all these weights that is getting tracked, there a simple mathematical equation will happen. Or I'll not say mathematical equation will happen, but there will be a technique that will happen which is called as matrix decomposition. That basically means the same 3x3 matrix is saved it in a 2 smaller matrix. Now in this 2 smaller matrix, you can see this is nothing but 1x3 and this is nothing but 3x1, right? Sorry, this is 3x1 and this is 1x3, right? So this is 3x1 and this is 1x3. When we multiply both these weights, then I will be getting this weight only, right? So over here, if I consider, I have some around 9 weights, 4, 5, 6, 7, 8, 9, right? You'll be able to see that I will be able to get all these 9 weights from how many number of parameters? Just 6 parameters, right? Because when we multiply this, then you'll be able to see that I'll get all these 9 parameters or 9 weights that I have, right? So in short, what LoRa is doing is that it is performing this matrix decomposition where a big matrix, and this matrix can be of any size, is decomposed into 2 smaller matrices based on a parameter which is called as rank. How to calculate a rank of a matrix? You can definitely check out any YouTube channel. It is a simple algebraic equations based on transpose of a matrix, how we calculate the rank. But let's say that this matrix that I have, which is a 3x1 over here, the rank of this particular matrix is 1, right? And if I use this 2 matrix, you can obviously see that the number of parameters that I'm storing over here is less when compared to this, right? Yes, there will be a loss in precision, but it is making sure that when we combine both this matrix, we'll be able to get the entire updated weights. And just imagine, start thinking, guys. Let's say that if I have 7 billion parameters, now I'm trying to perform fine tuning on those parameters. So whenever I track those weights, this huge matrix will be decomposed into 2 smaller matrices. And when we are decomposing this matrix, this updated tracked weights matrix into 2 smaller matrices, obviously we'll be requiring less parameter to store all these values, right? And this way, your fine tuning becomes very much efficient. And this really solves the resource constraint, right? This is the most important thing, right? And so in any research paper that you go ahead, you'll be seeing this equation. W0, this is my pre-trained weights, plus the tracked changed weights is nothing but my pre-trained weights plus B multiplied by A. What is B? B is this, A is this. So when we multiply this, you'll be able to see that we are able to get all the track change weights, right? And obviously this requires less parameter. If you are decomposing our bigger matrix into 2 smaller matrices, less parameters is required. Now what will happen if we keep on increasing the ranks? If we keep on increasing the ranks, this parameters will also keep on increasing, but it will always be less than this, right? If I have 7 billion parameters, if I try to decompose that into two matrices, 2 smaller matrices with increasing rank, then also the parameters that will be required will be less. How I am saying this? Because in the research paper also they have tried with multiple trainable parameters. Now let's see over here. There are multiple techniques of fine tuning. Some of the techniques that are there is something called as prefix embed, prefix layer, adapter. Adapter is one very famous thing that is probably used before LoRa, right? You can see as the rank is increasing, the parameters also increases, right? Initially, the trainable parameters are 175 billion, but when I use techniques like adapter, right? So initially it will have 7.1 million parameters with rank is equal to 1. But as I keep on increasing the rank, you'll be able to see that this parameters also get increased. But you can see from 175 billion parameter, if I compare 7.1 million weights, the percentage is very less. Now, similarly in LoRa, because of that matrix decomposition, you'll be able to see that as I keep on increasing my ranks, so these are my ranks with respect to Q, K, V, because in transformer you have this 3 parameter Q, K, V. There only all the matrix multiplication will happen with respect to these 3 parameters. And then as we keep on increasing the rank, here you can see 4, here you can see 8, here you can see 64. Then you'll be able to see initially we got 4.7 million parameters. Compare from 175 billion to 4.7 million. How this was possible? Because of the matrix decomposition. Because of the matrix decomposition, right? And as we keep on increasing the rank, you'll be seeing that the parameters are increasing, right? The parameters are obviously increasing, but if I compare it with 175 billion parameter, this is very less, 9.4 million. If you just see the percentage, right? So here also when rank is equal to 8, 37.7 million, then rank is equal to 64, 301.9 million, right? Parameters are there. So still, it is making sure that the parameter is not that much, like not like 175 billion or not near to this. If I talk with respect to percentage, it is very, very less. I've also made another table, right? Just to show you, if I have different models, number of trainable parameter. Number of trainable parameter. Here you can see I have one LLM model with 7 billion. If I use rank is equal to 1, then I will be having 167k parameters to fine tune weights based on fine tune weights. Then, and this 167k parameter basically means what? This decomposed matrix that I have, right? 2 metrics, that many number of parameters. So in the first case, it is just nothing but 167k parameters that is there available in this decomposed matrix. Okay. When we combine them, then we will be able to get how many? 7 billion parameters. If we combine both this matrix, then we'll be getting 7 billion parameters. Okay. Then similarly, you can see in 13 billion, then you have 2 to 8k parameters. In 70 billion, you have 5 to 9k parameters. In 180 billion, you have 849k parameters. So as you keep on increasing the weight, this parameters will keep on increasing, but it is not increasing with that huge amount, right? Even you can see when we keep the rank as 512, right? So here you can see 86 million parameters is there when compared to billions, right? Microsoft, it came up with this LoRa technique in one of the research paper, and it has used rank is equal to 8, okay, to probably do the fine tuning, and it has performed absolutely well. So most of the time we select this particular value, but at the end of the day, how to select this, right? It won't matter, because the parameters are increasing by very less number over here as we go ahead. So usually you can select rank 1, 2, 8 while you're performing fine tuning. Now, there may be also scenario that when should we use very high rank? When to use high rank? When to use high rank? This answer, because in the interview they may ask you, if the model wants to learn complex things, then you can specifically use high rank, right? Let's say some of the model is not trained to probably interact or probably perform some of the behavior. At that point of time, those complex things can be handled when you are probably increasing the number of ranks. Okay. So this can be a very simple question that may be asked in the interview. But I hope you got a complete idea. At the end of the day, this is the equation that you'll be able to see in most of the research paper. What LoRa is doing is that nothing. Very simple. All the track weights is decomposed into 2 smaller matrices with different ranks. It can be different ranks. When you're fine tuning, the first thing is that you really need to set that rank. Okay. If you set that rank, like in this particular case, if I go ahead and calculate with all the mathematical stuff, I will be able to get the rank is equal to 1. Okay. For this also rank is equal to 1, right? So similarly, if you have rank 2, so one of the matrix can be something like this. So decomposed matrix. So this is based on rank 2. Okay. So if I probably combine this, right? So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? If I multiply this, I'll be getting a matrix of much more parameters, right? But at the end of the day, in this particular case, it is less number of parameters, right? So this is what LoRa is all about. And because of this technique, the fine tuning is done less. The weights, the parameters becomes less. So this is how the main resource constraint is done. And with respect to all the downstream tasks, it becomes very much easy. Now, one more thing that I really want to talk about is QLORA. Okay. QLORA basically means quantized LoRa. Okay. Now you have already learned from the first video what is quantized. Quantized basically means, now in QLORA case, what will happen is that all these parameters that is probably stored in float 16-bit. Okay. We will try to convert this into 4-bit. That's it. Okay. Once we do this, you'll be able to see that we reduce the precision, and then we try to reduce these values also. By this, you don't require much more memory. So that is the reason we say quantized LoRa technique. Okay. And the best thing about is that QLORA also has one amazing algorithm which will be able to take care of both this part. Let's say if there is a float 16-bit, I quantize it to 4-bit, I can also convert this back into 16-bit. Okay. So with respect to this explanation, guys, I have already spoken about many things over here, LoRa and QLORA. Just to show you one example. So here is one example. I've already shown you this fine tuning using Google Gemma model. Let me talk about quantization. Quantization over here is basically done by bits and bytes config. So here it says load in 4-bit true. That basically means we are going to convert that entire model of 16-bit to 4-bit. Quantization technique that we are going to use is something called as NH4. And all the further fine tuning is basically done in vfloat 16. Okay. Now, there is also one more thing, right? See, LoRa configuration. Here we are selecting the first rank value 8, and then target modules where we need to apply this particular decomposition, and the task type casual LM. Once you do this and just execute, everything you'll be able to see it, right? And that is how the entire quantization and the LoRa happens. Guys, in this particular video, we are going to see the step-by-step way of probably fine-tuning your LLM models. In this case, I'm going to specifically take open source Llama 2 model, and with the help of a custom data set, we are going to fine tune this specific model, right? Over here, we are going to learn about various techniques practically, not theoretically, because if you really want theoretically, you can let me know in the comments section. So we will be discussing about something called as parameter efficient transfer learning for NLP, which is an amazing technique to basically fine tune all these LLM models, which will definitely be of huge size, like 70 billion parameters and all. So how this parameter efficient transfer learning actually happens, we'll try to see in the code. And we are also going to see a technique which is called as LoRa, right? So LoRa paper, if I go ahead and search, right, it is basically called as low rank adaptation of large language models, right? So these are some of the mathematical concepts. Don't worry, in the upcoming videos, I will talk about every theoretical intuition about PFT, about LoRa. Right now, a simple way of fine tuning, I'm just going to show you because many people were requesting for this, right? So initially what we will do is that we will go ahead and install some of the important libraries like Accelerate, PFT. As I said, PFT is nothing but parameter efficient transfer learning. Inside this only you'll find this LoRa technique, which is called as low rank adaptation of large language models. Then we have bits and bytes. Bits and bytes are specifically used for doing quantization. Now, what does quantization basically mean? All these LLM models, when they are trained with 70 billion parameters or 13 billion parameters, by default, the weights data types are in the form of floating values, right? When we say floating values, that they are basically 32-bit values. What we can actually do, and obviously, since I am actually going to do this in Google Colab, we get a very less RAM. So it is a better way that you quantize those weights, from float 32, probably convert that into int 8, and then probably based on the RAM size, you will be able to quickly fine tune it. Along with that, will also be using transformers, and then you have TRL. So all this libraries will go ahead and execute it, and once we specifically execute it, you'll be able to see that all these libraries will get installed. Now, in the second step, the major thing is that we will specifically be using the library called as transformers, which is specifically used for this particular purpose. And internally, we'll also be using PFT, which is having some LoRa configuration, and we'll use this PFT model. I know you'll not be able to understand what exactly PFT is, but I'll just tell you in some time. Just let me go ahead with. But at the end of the day, PFT actually uses techniques which will try to freeze, when it applies transfer learning on these LLM models, it is freezing most of the weights of that LLM model, and only some of the weights will be retrained, and based on that, they will be able to provide you accurate results based on your custom data set. Okay, how it is done? Don't worry, I'll create a amazing dedicated video to make you understand this mathematical intuitions. Okay. Now over here, you will be able to see that I'm going to import OS, import torch. I'm going to use a data set. I will talk about what data set we are going to specifically do the fine tuning, but here we are specifically using open source LLM models. And then from transformer, I'm going to use auto model for casual LLM, auto tokenizer, bits and bytes. I will talk about all these libraries as we go ahead. So let me quickly go ahead and execute it. Okay. Now, till this is getting executed, this import statement is getting executed. Let's talk about some of the important properties over here with respect to Llama 2. In the case of Llama 2, the following prompt template is used for chat model. So this is the specific prompt template. Here we give an instruction in this S symbol, and then we have our system prompt, which will be closed with the sys brackets. And then you will also be able to give your user prompt over here, and the model answer will be coming after this entire instruction. Okay. So this is how the entire Llama 2 models, LLM models specifically require the system prompt and the user prompt and the model answer format, right? Now, any data set that you specifically get, right? We really need to convert that data set into this format. Okay. And that is how I will show you how to probably do this. There is a technique. You can also write your own custom code and all. There are many ways. Okay. Now what we'll do, we will reformat our instruction data set to follow Llama 2 template. So right now we are going to use this data set, which is basically called as Open Assistant Guanaco. I hope I'm pronouncing it right. Now here you will be able to see this is my data set, right? Human, can you write a short introduction about the relevance of term monopsony in economics? Please use example related to this. And then monopsony refers to the market. So here you can see assistant answer. So here the data set is basically in the form of human and assistant. Like human has a question over there and assistant is probably providing you a specific answer. So in this format, you'll be able to find out each and every rows in different languages. So we are going to take this entire data set, and then considering this entire data set, what we are going to do, we are going to reform the data set following the Llama 2 template. And out of all these samples, all this data set, there are around, how many data sets are there? I guess there are around 10K records. We are just going to take 1000 records or 1K records. The reason is that I really need to show you how the fine tuning is basically done. So if I go ahead and click on this, and if you see this format, right? This format, you will be able to see that this entire data set is converted in this format only, right? Instruction is basically there, the answer is over here, and this entire S is getting closed, right? So all the data set is basically converted into that specific format. Now, how do you convert it, right? So for that, already what we have basically done is that over here, to know how this data set was created, you can check this notebook. So this notebook is there already. You can see that we are loading the data set, we are applying this, we are taking the 1000 records, and then we are transforming, right? So in transforming, basically a simple Python code, like I have to probably keep in that specific format, right? So that is the reason I'm showing you this specific code over here. Just by one click, you will be able to do that. Okay, so all the links are actually given. Now you need to follow. Now understand, guys, see, understanding how the specific techniques are, definitely I'll create a dedicated theoretical video understanding all the maths equations that is required, right? Over here, we are trying to see that how you can also run your own fine-tuning model, right? So note, you don't need to follow a specific prompt template if you are using the base Llama 2 model, but right now we'll not use this base Llama 2 model. Okay, how to fine-tune Llama 2? So these are some of the steps. Not only with Llama 2, with other models also this will work. But again, there the format may change. You know, the format of the instruction, the format of your prompts may change. So free Google Colab offers a 15 GB graphic card, right? So limited resources, barely enough to store Llama 2 7 billion weights. Now here we are going to use 7 billion weights, but it is also very difficult to store 15 GB, right? Whatever free model that we specifically have. We also need to consider the overhead due to optimizer state, gradient, and forward activation. Okay. So usually in any LLM models, you will be having gradients, you will be having forward activations, you'll be having optimizers. So there also you require some amount of memory. Fine tuning is not possible here, right? Obviously this will not be possible because 7 billion weights, you cannot store it in 15 GB. That is the reason we require this parameter efficient fine tuning technique. Now, what does PEFT basically do? It is going to freeze most of the weights that is present in that LLM model like Llama 2, and only with some of the weights after applying quantization, it is going to probably perform the fine tuning. Now, parameter efficient fine tuning, my next video, I will talk about this research paper. If you quickly want this video, please make sure that you make the video likes to 1000. Okay. Now, what we are going to do over here, we are going to use techniques like LoRa and QLORA. As I said, LoRa or QLORA. LoRa is nothing but low rank adaptation of large language model. Again, apologies guys, if you don't know the mathematical concepts, I will explain in the upcoming video. Okay. So first of all, we will load a Llama 2 7B chat GPT model, this chat HF model, then train it on this 1K sample, which will produce a fine-tuned model with which in the name of chat fine-tune. We'll try to create in this. QLORA will use a rank of 64 with a scaling parameter of 16. We will load the Llama 2 model directly in 4-bit precision. We are trying to convert that 32-bit into 4-bit. So that is how we are going to do the training. And with respect to QLORA, in order to find the low rank index, we are going to use the rank of 64, right? This is an hyper tuning parameter. You can just consider right now, this is a kind of a hyper tuning parameter with a scaling parameter alpha. This is also called as alpha. It will be having a scaling parameter of 16. As I said, everything will be explained detailedly when I probably go with the mathematical equation. But right now, our main aim is to probably learn how to fine tuning it. Now, what model we are going to use? We are going to use Llama 2 7B chat HF. Then the instruction data set to use is this particular data set. We will be downloading it from the Hugging Face. The model name also will be downloading it. And after fine tuning it, this will be my new model name. Okay. Now, these are some of the QLORA parameters that is required. Okay. So one is LoRa underscore R 64. What is this R? This R is a rank of 64, a kind of a hyperparameter. LoRa alpha, as I said, alpha, right? I told you alpha. Why? Because I know the entire mathematics stuffs in this. Okay. Just to increase the curiosity, I'm coming up with this first video and later on I will come up with that. Then here also dropout is basically required. Now, in order to do the quantization, we will be using bits and bytes parameters. So here you can see activate 4-bit precision based model. So there is a parameter which is called as use underscore 4-bit, which is equal to true. Then compute data type for 4-bit base model. So here it is basically float 16. Then quantization, we are using FP4 on NP4. So BNB 4-bit quant type, you have to keep this particular value to NP4 since it is 4-bit. Activate nested quantization for 4-bit base model. So here we are keeping it as false. Now understand guys, these are some of the basic parameters that we specifically use in LoRa technique, specifically in PEFT. Then training argument parameters, our output directory will be present in this results. I'm going to run one epoch. Then we are going to enable this FP6 and BF16 training. Okay. It is set to true with an A100, right? So A100, you can set it, if you are using A100, you can set it to true. Right now I'm using T4. If you have the paid version of Google Colab, then you can set it to true. Batch size for per GPU for training. I hope you know what is batch size. Then you have GPU for evaluation batch size. Then gradient accumulation step, checkpoints, max grad norm, learning rate, weight decay, right? Optimizer, page ADAM-W we will be using, which is of a variety of ADAM itself. Then learn LR scheduler type cosine, because it works on similarity, right? Whatever question and answers we specifically write. Then maximum steps is -1 number of training steps, override number of training epochs. And after this, you are also putting logging steps is equal to 25. Now, with respect to any fine tuning technique, you use something called as supervised tuning, right? In supervised tuning, that is, you require some parameters, right? Max sequence length, then packing, then device map. So this is load the entire model on the GPU 0, right? So this is what are some of the parameters. Don't worry, these are some of the parameters that you don't need to learn each and every parameter, because already all these things are provided by the official page itself. I've just copied and pasted it over here, right? So we will go ahead and execute it. So let's go ahead and execute it. So all these parameters are set. Now the step 4, right? There are multiple 4 steps, right? One more step is there later on. Load everything and start the fine tuning process, right? First of all, we want to load the data set we defined. Here our data set is already pre-processed, but usually this is where you should reformat the prompt, right? Filter out bad text, combine multiple data. Some amount of pre-processing is required, but already we have done that, so we are not going to do it. Then we are configuring bits and bytes for 4-bit quantization. As I said, right, from 32 or 16-bit, we are converting that into 4-bit so that it requires less space with respect to GPU for the fine-tuning purpose. Next, we are loading the Llama 2 model in 4-bit precision GPU with the corresponding tokenizer, right? With that tokenizer, we'll try to load that, and obviously we'll also be loading it with the 4-bit precision. Finally, we are loading the configuration of QLORA, and passing everything to the SFT trainer. So here is what self fine-tuning, this SFT will basically happen, right? Now let's go ahead and let's do this. So first of all, we are loading the data set. We are loading the tokenizer model with QLORA configuration. So here I have written this BNB compute D type, and we are using torch. So along with that, you also require bits and bytes config. Again, load, we are enabling this 4-bit. Then all the necessary parameters like compute D type will be using Houston nested quant. Okay. Again, I'm telling you guys, there is nothing new to learn in this because all these formats will be available in the official documentation. Then we are going to check the GPU compatibility with float 16. If compute type is equal to torch.float16, use 4-bit. Otherwise, these all things are there, right? Then we are going to load the base model. See, whenever we want to load the base model from Hugging Face, we can use this auto model for casual LM, right? That is the reason we have imported on top. Dot from pre-trained model name. What is my model name? I have given that quantization config. So here you'll be able to see in quantization config, we have also given something called as BNB config, right? So here you'll be able to see this is the compute type. Let me just search for it. Somewhere here only it will be available. So BNB config. So here you can see this entire bytes config is basically there. So based on that, you'll be okay. Yeah, compute app. Okay. Yeah, perfect. So BNB config is basically given over here. Then device map is nothing but with respect to the GPU we are mapping. Then model.config.use cache false. You can also make it true if you want. Model.config.pretraining_TP is equal to 1. Then we are loading the Llama tokenizer. See, for any LLM model, we also need a tokenizer so that it will be able to convert any LLM model, the input data that we are specifically using into word embeddings and all. So that is the reason order tokenizer from pre-trained. Again, model name, we are going to use this. Trust remote code is one additional parameter that is used. Then we are going to put a pad token with respect to the end of statement token, right? So this .eos underscore token specifically applies the token for the Llama itself, right? And here we are giving the padding side as right. Fixed weird overflow issue with FP16 training. All these parameters will be almost fixed, guys. Only thing that you will probably be changing is with respect to the configuration. Then load LORA configuration. Here you will be able to see PFT config, LORA config, all the values that you are putting with respect to this LORA configs. And yes, here you have your PFT configuration. Now this is the most important thing, because in this training arguments, we had set all the parameters: output directory, number of epochs, this, learning rate, FP16, BS16, you can probably see over here. And then finally, we are reporting it to the TensorFlow, right? Tensor board. Then you can also see that supervised fine tuning parameters, right? I'm giving my model name, I'm giving my data set, my PEFT config, my data set text field. This PEFT config has a LORA config, right? Then you have a tokenizer, you have the arguments, you have packing, then you have finally trainer.train. Okay. Now this is what is the main thing. And that is where your supervised fine tuning will happen. Step by step, we have done it. Okay. Again, let me repeat it quickly. We have loaded the data set. We have set our D type, right? We are setting up all our quantization process over here. Here we are checking whether the GPU is compatible or not. Here we are loading our LLM model, that is Llama 2. Here we are specifically loading our tokenizer, which is really used in Llama 2. Along with this, we are putting padding techniques. Then my LORA configuration, which will specifically be in terms of PFT config. And then all my training arguments will go inside this, right? This training arguments is with respect to where my output directory is and all, learning rate and all. Okay. Finally, set supervised tuning parameters. Here we have set it model, dataset, PFT config, text, max sequence length, tokenizer, everything is put up over here. And finally, we go ahead and train this. Now, once we train it, it is going to run for 250 epochs. I think 250 step size I have actually given over here. Sorry, 25 steps, logging steps. Let's see what is the batch size. Batch size is 4. Yeah, till that much it will probably go. So let this start. So it has already started, I guess. So here you can see it is downloading. Here you will also be able to see the data set. Okay. Sample data right now you cannot see it because the data set will get loaded. Okay. So table of contents, install all the required packages, we'll reformat. All the steps are given side by side. You can also read it out. I know this looks like a little bit tough, guys, but at the end of the day, I'll not say that it is easy. And just the reason why I'm sharing you this fine tuning technique, because you should just get in your mind later on, you know, this is the pattern that I'm following. First, execute this. Don't worry about anything as such. Just try to get a high level overview how things work. Later on, I will try to break down each and everything in my next video by breaking this entire code, why this specific parameters is used. Because the main thing is to understand what is PEFT, what is quantization, what is precision, and how do you specifically use this PFT technique, what is QLORA, everything, what is low order rank index, how to basically calculate that, everything I will talk about it. Okay, so we will wait for some time. Till then, just let us wait, and I'll just come again. I think it will take 15 to 20 minutes to complete this entire fine tuning with 1000 records. And then again, I'll come back and we'll start doing and seeing whether we are able to get the good results or not. So yes, let's wait for some time. Thank you. So guys, finally you can see here the 250 epochs or 250 steps have completed. It took 25 minutes. And again, this is in Google Colab. If you have paid version of Google Colab, it will probably take hardly 5 to 10 minutes to complete. Okay. So over here, you can see the global step was 250, training loss, it went till 1.36, metrics, runtime, everything, training samples per second, all this information is basically done. Okay. And please remember this particular word, which is called as floss. Okay. Total floss, because I'm going to discuss about this in my next video also. Now, once we do this, we are going to save this trained model, right? And understand the new model name, what it will be, right? So here you can probably see Llama 7B chat fine tune. So this is my results with respect to run. All the results you'll be able to see over here also. Okay. So here in this fine tuning technique, it is also creating something called as adapter model. Okay. Please remember these words, because in the next theoretical intuition, we are going to discuss each and everything as we go ahead. Okay. So please make sure that you remember it. So we are going to save this model. So we have written trainer.model.save.pretrain model. Right now, you can also check out in the tensor board, but I will just go ahead and show you quickly that how it is probably going to generate it, right? So here we have created a prompt, which is called as what is large language model. I've used pipeline, right? So this pipeline, we have already imported it. The task will be task generation. Whatever model we have actually created, that model will be there. Tokenizer will be used over here, and max length we can keep to 200 to 250. The result, and always understand, as I always suggested, with respect to Llama 2, this will be my format. There will be an S, then there will be an instruction. And here I will be having my prompt. And with respect to this particular prompt, we are going to get some kind of response. So whatever response we are going to get inside this result variable, it will be in the form of list. And inside that, there will be one field which is called as generated text. So if I go ahead and search what is large language model, you'll be able to see that how we are going to get the result. Okay. Because we are running the same model over here. So here is my prompt. Here we are using pipeline. Pipeline basically helps you to combine multiple things like task, model, tokenizers, multiple things that will be able to give you, right? Now, since this is already running in this particular collab, and obviously you'll be able to see RAM and all are almost, it is used the disk space of somewhere around 39 GB, right? So just wait for some time, and here you will be able to get the response. If you quickly want to get the response, obviously you need to have a good GPU, right? Because based on that, it will be able to give you a quick result, right? So after that, you'll be also able to see that we'll be able to delete all these VRAMs and all. Okay. So let's see, and let's see whether we'll be able to get our result. In the next step, we can also push our model to the Hugging Face, which I will keep it right now. I will not explain it, because this I will show you as an complete project as we go ahead. So here you can see what is large language model. A large language model is a type of artificial intelligence. Large language model often seen. Then here you can also see all the information are there. Some example of large language models are include this. Okay. Now what we are going to do, let's go ahead and take any one example over here from this particular data set. Okay. So I will just write how to own a plane in United States. Okay. So this will be my over here, and I'll paste it over here. Let's see. So this will also run, and I will finally get my result also. So same question I've taken, right? So from this 1K result, so to own a plane, this is the answer that we will probably be getting. Let's see how much time it will take to probably showcase. But always remember, please keep on looking at this particular RAM, like how much time it is probably taking and how much space it is taking. Okay. So guys, here you can probably see the response, how to own a plane in United States. In United States, owning a plane is this, determine your budget. So this is completely based on this information that is present over here. But here I've written only 200 max length. So I can only see 200 characters that is given, right? So you can probably try with each and everything as you go ahead. One of the most interesting thing in the field of data science or generative AI is that the kind of research that is currently happening, right? Every day you'll be seeing some new things that are actually happening, which is very much beneficial for the entire community who are working with LLM models. Specifically today, I saw this amazing research paper where it is written as era of 1-bit LLM. So I'll be going to talk about this particular research paper and what exactly 1-bit LLM is and how it is far more advantageous when compared to those 32-bit or 16-bit LLMs models. Okay. So everything I'll be discussing about. One important thing that I also want to make sure that you learn from this particular video is that how do you read a research paper? What are the important points that you should definitely highlight while reading a research paper, and how you should and one thing is that you cannot directly understand just by reading it. You really need to have some basic knowledge, and without that particular basic knowledge, it will be very difficult to understand. So if you're following my tutorials, I always make sure that whenever I make my videos, right, I definitely watch or see all the research papers. And then with respect to that, I simplify those concepts and try to explain it to you. So let's go ahead and understand about this 1-bit LLM. Now guys, if you remember in my previous video, we have already discussed about quantization. Right. So quantization was covered. Now with respect to quantization, what we were doing is that, let's say I have a model which is called as Llama 2, which is an open source model. Let's say this model is having 7 billion parameters. When we say 7 billion parameters, I'm talking about weights. Okay. Now, obviously, if I have a system where I don't have very high configuration, I have resource constraint, I have limited amount of RAM or GPUs, what we specifically do, we perform quantization and we convert this Llama 2 model, which is probably in FP 32-bit, and we try to convert this into int 8-bit. Okay. Int 8, which is nothing but 8 bits, right? Now, once we are doing this specific process, what is basically happening is that the model size is getting decreased, right? And because of that, we will be able to load it and we'll be able to perform any task. Along with this, we can also perform fine tuning with the help of LoRa and QLORA, right? So I hope you know this LoRa and QLORA. I've already discussed in my previous video. Please just go click on my channel. Otherwise, just go ahead and see in the description. I've been providing that particular links with respect to fine tuning. Now, with the help of LoRa and QLORA, we can perform the fine tuning. Okay. Now, the question is that what is this 1-bit LLM, right? As I said that with the help of quantization, we will try to convert this into 32 to 16-bit, or it can be 8-bit, right? But converting this into a 1-bit, that can be again, now just by seeing this, right? If we are able to convert this into 1-bit, that basically means we will never be having any resource constraint, right? Resource constraint, yes, with limited RAM, with limited GPU, with limited storage, we can probably perform everything from fine tuning to inferencing, right? So inferencing can also be performed, right? And this is what is so amazing about this. And this is, I don't know, like what is going to happen just in some days, because once this is probably gone, right now we just have the research paper. Once this implementation gets started, trust me, it will be quite amazing for the entire community who are working with LLM models. Okay. So this was just a brief idea about this one. Now let's go ahead and discuss what is 1-bit LLM. Okay. And when we say, to be precise, when we say that all large language models, it is basically in 1.58 bits. Okay. Why it is 1.58, we'll discuss about it. And there are many points that needs to be discussed. Along with me, please make sure that you watch this video till the end, because I'm going to read over here, because this will also give you an idea that how you should probably go ahead and read the research paper. So let me quickly go ahead and clear this. Let's see whether it will be getting cleared or not. Okay. So over here, okay, clear is basically happening. Okay, I will just rub it. Okay. Now let's go ahead and discuss about this, and let's read some of the important information that is present over here. Okay. And trust me guys, read along with me. Then only you'll be able to understand how you can read the research paper. Okay. Now, what exactly this 1-bit LLM model is? In this work, we introduce a 1-bit LLM variant, namely BitNet. Okay. So BitNet is the LLM model name, 1-bit LLM model name. And then where every single parameter or weight of the LLM is ternary, right? Now it is not floating 32-bit, 32-bit or 16-bit. It is ternary. Ternary basically means it has only 3 values. It can have only 3 values, weights. It can be -1, 0 or 1. Okay. It matches the full precision transformer M with the same model size and training tokens in terms of perplexity. Perplexity basically means, so with respect to any query that I ask, an end-to-end task performance, right? While being significantly more cost effective in performance of latency, memory, throughput and energy consumption. So obviously, at the end of the day, all the LLM model will specifically have this kind of constraint, right? Which are specifically with huge number of parameters, let's say 7 billion, 170 billion, right? And if you're just using these 3 numbers, -1, 0, 1, you'll be able to understand why I'm saying that because of this ternary values, right? You'll be seeing how abundance the performance improves. Okay. So furthermore, so here you can probably see all these points, latency, memory, throughput and energy consumption. Energy consumption can be with respect to inferencing, with respect to fine tuning and all. Okay. Now let's understand how this operators, how these values will be basically used. Okay. This is also important. So with respect to this, what I am actually going to do, I am going to make sure that to explain you, I take the right thing. Okay. So let's understand this. Okay. Understand guys, whenever we talk about parameters, these are my weights. Okay. These are my weights. Let's see. So these are my weights. Okay. And these are my weights. So let's consider that my initial transformer LLM weights is this one. Okay. Now when we say 1-bit LLM, we are going to convert all these values and replace them with either of these 3 values, -1, 0, 1. Okay. So that is the reason that you see over here, all these weights is getting converted into something like this. Okay. -1, 0 or 1. Only that 3 parameters is there. Okay. And this is what we basically say as BitNet B 1.58. Okay. And this is also called as Pareto improvement. How this is basically happening, I will talk about it. Okay. Just give me some time. There will be some kind of quantization getting applied here also. Okay. Quantization getting applied over here. Okay. To convert these values to this. Okay. Now let's understand one very important thing. Okay, and this is the most important thing. What will happen if we convert these values to this? See, with respect to any fine tuning or forward propagation and backward propagation, what exactly happens? The model weights over here is basically getting multiplied by the inputs and then we get the output, right? Yes, additionally we add a bias, so it's okay. We don't include a bias right now over here just to show it to you. So over here, let's consider that this is my floating point 16 number. So every number will get multiplied by the input, right? And then what will happen is that after that, it's just like this, right? Summation of I is equal to 1 to n, w of x plus b, right? So this is what is the operation that is basically happening. Whenever we do the forward propagation, whenever there is an updation of weight, that basically means we are doing the summation of weights and the input, right? So once we are doing this and then we are doing the summation, okay? But if we have all these weights in the form of -1, 1, 0, then what will happen is that over here you'll be seeing that multiplication operation will not be that much valuable, right? So over here, first of all, we are doing multiplication, then addition. But over here, we are just doing addition, no multiplication. Because any number it will be multiplied by 0 is 0 only. Any number that is multiplied by 1 is 1 only. Any number that is multiplied by -1 is -1 only. So over here, the main thing is that your addition operation is only happening. Addition operation is only happening. Now, obviously, if you only need to do addition operation, then what will happen? Your GPU will not be requiring that much GPU also. So your GPU will also get reduced. Why this operation takes more GPU? Because multiple multiplication needs to happen, right, with respect to different weights, right? Then addition of all those values needs to happen, because in the forward propagation, this is what is the equation that specifically happens, right? We multiply by the weights with the inputs, and then we do the summation, and then finally we add the bias, right? So this is the most important thing. So here you will be able to understand with floating point 16, right? All the numbers is first of all multiplied by the inputs, and then the summation is done. But here your values are with respect to ternary, that is -1, 0, 1. So here multiplication is already skipped, because 1 into x0 is x0 only, right? It is a simple multiplication, right? And that much resources will not be required for simplistic multiplication. So here maximum to maximum only addition will be required, right? So I hope you are able to understand, because of this technique of Pareto improvement, you'll be able to see that what we are able to achieve, right? And obviously when we are able to achieve this, the GPU will be required less when we are doing the fine tuning or training, right? So I hope you have got this as a complete idea, and you have understood, right, why we specifically do this, how it is done, how this transformation is done. So here you can probably see that it provides the Pareto solutions to reduce inferencing cost, latency, throughput, and energy of LLM while maintaining the model performance. The new computation paradigm of BitNet 1.58 calls for action to design new hardware optimization for 1-bit LLM, right? I know, guys, this is more of a research paper, so I'm reading and I'm telling you each and everything and also explaining you the concept. I know this can be a little bit of boring, but trust me, you need to understand in this specific way. Okay, now let's talk more about this, and I've highlighted main things in this green color. Okay, these models have demonstrated remarkable performance in a wide range of natural language processing tasks like LLM models, but their increasing size has posed challenges for deployment and raised concern about the environmental and economic impact due to high energy consumption. Obviously, this is the problem with LLMs that are already available. One approach to address the challenge is to use post-training quantization to create low-bit models for inferencing. I've already discussed about this quantization, LoRa, QLORA, everything. This technique reduces the precision of weights and activation, significantly reducing the memory and computational requirement of LLM. The trend has been to move from 16-bit to lower bits such as 4-bit variant. This is what is basically happening with respect to LLM models, right? This is with LLM, okay? This is with LLM. So here I'll write LLM models. Now let's see, with the help of 1-bit architecture, 1-bit model architecture, what we can solve. So recent work on 1-bit model architecture such as BitNet presents a promising direction from reducing the cost of LLM while maintaining the performance. Vanilla LLMs are in 16-bit floating values, and the bulk of LLM is matrix multiplication. Therefore, the major computation cost comes from floating point addition and multiplication operation. I said you just now on top of it, right? In contrast, the matrix multiplication of BitNet only involves integer addition, because anything multiplied by 1 is 1. Anything multiplied by 1 is that same number. Anything multiplied by -1 is that same number with a negative sign. Anything multiplied by 0 is obviously 0, right? So as the fundamental limit to compute performance in many chips is power, the energy saving can be translated into faster computation. Now this is the most important thing, right? And here you can clearly see the things that I've highlighted, right? I hope you get an idea how good this 1-bit LLM can be, okay? Then you can still read about it. Here we are going to just use ternary values like -1, 0, 1. And obviously, because of this 0, your 0.58 bit is basically increasing. There are two major advantages of using this also. It is written over here. See. Furthermore, BitNet. Oh my God. Why this is getting highlighted like that? Okay. Furthermore, BitNet offers two additional advantages. First, its modeling capacity is stronger due to explicit support for feature filtering. How feature filtering is happening? Because anything multiplied by 0 will be 0 only, na? Right? made possible by the inclusion of 0 in the model weight, which can significantly improve the performance of 1-bit LLM. Secondly, our experiment shows can match full precision baseline in terms of this end-to-end task performance starting from a 3B size. Okay. Now, most of the things that you are able to see, right? Now, let's discuss about one more important thing. That is how this transformation is happening. How these numbers are getting converted to this. It is just by using this simple mathematical equation or this quantization function. Okay. Quantization function. Okay. And this quantization function is called as absolute mean quantization. And this is the formula that is basically used by which all the numbers are basically getting converted to only this 3 values. Okay. 0, 1. Okay. 1, 0, 1. Okay. Just by applying this particular formula. Okay. So and there is also one more change with respect to the transformer. It replaces nn.linear with bit linear. Okay. So this bit linear, I think you will be able to see that it is trained from scratch with 1.58 bit weights and 8-bit activation. So this is what it is basically done with respect to the initial training. Okay. So most of the thing I have actually discussed over here. Let's talk about the performance. So over here you'll be able to see that the Llama model of 700 million parameters, BitNet will also have 7 million parameters, but here you see the memory is decreasing, right? Over here 2.08, 1.18, 12.33 is getting reduced to 0.80, 0.96, and then this PPL is basically 12.87. So over here you can see that how it is getting reduced. Now similarly, when the billion of parameters are basically increasing, right? Let's say with Llama is 1.3 billion, right? The parameter will be same, but memory again 1.14 is required, 0.97, 11.29, right? And similarly over here also you'll be able to see the same thing is basically happening. So memory is decreasing, latency is also decreasing for the inferencing purpose. Perfect. And one more parameter that you'll be able to see with respect to model size and latency, right? Model size. So the blue color is basically the Llama model. Okay. The orange color is basically 1-bit LLM models. You'll be able to see how much huge latency difference is there. Similarly, with respect to this, how much huge memory difference is there, right? To save this kind of models. So this is just the research paper that has come up recently, but I'm really happy to see this because in the future, many things is going to happen. So again, I would like to welcome you all to the era of 1-bit LLM models. And now you'll also be able to use this 1-bit LLM model soon. I think first of all, Hugging Face will only come and try to implement all these things where you can also easily create your application using generative AI. So guys, Google is again on bang and it has created its own open source LLM model that is called as Gemma. Now again, it is on that specific race of open source LLM models also. Till now, the most accurate model that we specifically had was from Meta, that is called as Llama 2. Now Gemma is there. In this specific video, we'll try to see a practical application. Along with that, we'll try to fine tune with the help of this specific Gamma model. Okay. So what exactly is Gamma model? I'll just show you one blog. First of all, why they have actually created it. At the end of the day, all the companies, is saying this thing, right? So Gemma is built for responsible AI development from the same research and technology used to create Gemini models. Okay. At Google, we believe in making AI helpful for everyone. We have a long history of contributing to open source communities such as Transformer, TensorFlow, BERT, T5 JAX, AlphaFold, and AlphaCode. Obviously, Google is doing, I think it is from past so many years, it is doing so much of research, specifically in open source contribution. It has given TensorFlow, it has given many things as such. Along with that, Meta is also in the same race. Both are doing fabulous job. So let's go ahead and let's know more about Gamma. Gemma. We'll say Gemma. Okay. Gemma also we could say. I don't know how to pronounce it, but it's fine. So if I probably talk about this, the main thing that you really need to know is about the performance metrics. Over here, when I compare, see, two models are there with respect to this particular model. One is 7 billion parameter, one is 2 billion parameter. If I consider with respect to Llama 2, we have 13 billion and 7 billion. With respect to all these things, I think Gamma is performing absolutely fine. Here you can see that it is having 64.3 with respect to various benchmark accuracy. If you want to know more details about it, you can actually see this particular blog. Over here, if we are just comparing open source models like Gamma and Llama 2, Gamma is way forward when we compare with respect to the 7 billion parameter it has, right? 64.3, the general accuracy reasoning is 55.1, 81.2, math 46.4. It is far, far better than the Llama 2 models also, right? So this looks absolutely great. Here the accuracy is also very, very good. Now let's see more about it. It is specifically used for research purpose. You can also use it over here. You can build your own models. And the other thing is that right now, the Gamma 2 models, right, 2 billion parameters, 7 billion parameters, already available over here. See, in Hugging Face. So once you probably go to Hugging Face and search for Gamma 7b or Gamma 2b, you'll be able to see this kind of page. Here, you need to get granted to access this model. So here they'll tell you to probably check the terms and conditions to get the license of this particular model to use it. Okay, so it will be like a checkbox. You just need to check it. I understand that and give the confirmation, right? Once you probably do that, you will be able to get the access of this specific model. What is the main aim of this particular video? I'll try to show you with the help of practical implementation how you can access this particular model and how you can actually use it. So now let's go ahead and let's see this fine-tuning technique with the help of Google Gemma model. And again, guys, this is just a simple use case that I've taken over here, but you can do some amazing use cases with the help of this. And that is what I'll plan in the future. Some amazing use cases that I've already developed with paid OpenAI models. I'll try to also develop that with this along with fine-tuning. Okay. So initially, what we are going to do, we are going to see this Google Gemma model, how it performs and what kind of task, all that kind of NLP task you'll be able to do it. Okay. So initially to go ahead with, I will go ahead and install all these libraries, that is bits and bytes, PEFT, TRL, accelerate, datasets, and transformers. If you don't know, guys, I've already created a video with respect to fine tuning. Okay. Now in fine tuning, what we have actually done, we have done the fine tuning with the help of Llama 2 model. Okay. So let's see, a UTF local is required. Let me restart my kernel. Change runtime, disconnect and delete runtime. Okay. So let me go ahead and reconnect it and then we will try to do the installation again. But I've already created a fine-tuning technique with the help of Llama 2 model. The same steps and process will basically happen over here also. So okay, it's got connected. Now let's go ahead and do the pip install. So here you'll be able to see the pip installation will specifically happen with all these libraries. To just tell you what we are going to do, this bits and bytes techniques, bits and bytes libraries used for quantization purpose. I've already created a video with respect to quantization. What is the main aim of quantization? Quantization actually allows you, let's say that you have a huge model, right? Right now we have this Google Gemma model of 7 billion parameters or 2 billion parameters. If I want to load it, let's say in Google Colab. So in Google Colab, right now I have somewhere around 50 GB RAM or 201 GB hard disk, right? And right now I'm using this Google Colab premium version, right? Let's say if you are using it, you'll hardly get 15 GB RAM. It is not possible to load that entire model over here. So what quantization techniques helps you do is that it helps you to convert that float 32-bit, right? Usually all the numbers, all the weights, right? All the bytes are saved in 32 bits. It will help you to convert that into 8-bit, 16-bit. So when you convert that, you require less memory at that point of time, right? So that process is specifically called as quantization, and I have actually explained it. I've shown you how mathematically we specifically do quantization. So everything is explained in this particular video. I'll provide you this link in the description of this particular video. Now the next thing is that we will be importing some important libraries. One is OS, transformers, then you can probably see Torch, Google Colab user data, datasets I'm going to load it, SFT trainer, PEFT, right? PEFT PEFT, LORA configuration. As I said that we are going to use LORA technique, okay? SFT trainer is specifically used for fine-tuning purpose, supervised fine-tuning, we basically say. Right now from transformers, we are also going to use auto tokenizer, because tokenization, if you want to really perform tokenization while fine tuning, we'll be using this auto tokenizer so that it can load based on the model that we have. Then you have this auto model for casual LLM. This is specifically used so that we'll be able to fine tune with respect to casual large language model. Okay. Then from transformers, we are also going to import bits and bytes config. Here we are going to give the configuration with respect to quantization. And then we have this Gemma tokenizer. So let's go ahead and import all these things. So Gemma tokenizer is something for the Gemma model itself, right? So a tokenization technique. Otherwise, you can also use other tokenization. It is not necessary that you always need to use Gemma tokenizer. Now let me tell you one more step. The next thing is that after importing all this, you know that this Gemma 7b model is specifically present in Hugging Face, right? Now, in order to access this model, in order to download this model, we really need to have something called as access token. Access token of what? Access token of the Hugging Face. So how do you get an access token? Go over here, click on settings, and here you'll be having something called as access token. Just copy this, okay? Copy this access token, and once we have this access token access, right, then only we'll be able to download the model from here. So here, what we will do, go ahead and set it in the Google Colab. How do you set it? Click on this key button. So everybody will be having this key button, and just click on add a new secret. And I have written it over here as hf_token with that same value that I have copied from there. So once I probably write it down over here, so this is basically saved, right? So this is saved over here. Now, once I've saved it, any number of notebook that you specifically work in, you will be able to access this Hugging Face token. How do you access it? It is in simple. os.environment hf_token is equal to user-data.get hf_token. You just need to write user-data.get hf token. So once you do that, it will ask you for the grant. You just need to grant it, and then it will be able to access, and it will be able to also identify which Hugging Face from which username or password or which username you are specifically pulling that particular information. Okay, so this is done, right? Now through this, you will be able to access any models from the Hugging Face, right? Let it be Llama 2, any model that you specifically want to use. Now what we'll do, we will go ahead and call this particular model Google Gemma 2b. Initially, I showed you 7b, right? I'm going to load it 2b, right? 2 billion parameters, not 7b. 7b also you can do it. It'll still take time for the fine tuning purpose. Now here you can probably see I've taken this, and then I've written bytes BNB configuration, that is bits and bytes configuration. The first parameter is load in 4-bit is equal to true. That basically means what? My model, the Gemma model in 2 billion parameters is specifically in the 32-bit, right? Initially, we are trying to convert that into 4-bit, and this process is specifically called as quantization, right? So what we are doing is this, once we set it in load in 4-bit, all the activation functions, all the weights that are stored in 32-bit will get converted into 4-bit, okay? Now the second parameter that you'll be able to see, BNB_4-bit quant type is equal to NF4. What is NF4? 4-bit normal float. So the quantization technique, how do you convert this into a 4-bit, is basically taken from this particular parameter. If you really want to know about it, I've given a link over here. What is 4-bit quantization and how does it help Llama 2? The reason why I've written Llama 2, because we are talking about open source model. Then you have BNB 4-bit compute type, which is nothing but torch.bfloat 16-bit. Now the reason we have kept this as 16-bit, see, this we are performing quantization. That basically means we are taking a big model, we are making it a small model. How? By performing quantization, by converting the 32-bit into 4-bit. Now, along with that, whatever fine tuning takes place, for those fine tuning, all the weights that gets updated will get updated with respect to this particular 16-bit. See, there is some loss of information with respect to quantization. To balance that, we are keeping the new fine-tuned parameters in 16-bit. So that is the reason we have written it over here. So once I execute this, so this is my model ID, this is my configuration. Now, based on this model ID and configuration, I am going to use the tokenizer. And from this particular pre-trained model, I'm going to call the tokenizer. And for here also, I'll be using the HF token. Okay. Then you have model. Over here, order model for casual LM from pre-trained. Model ID, we'll use this model ID. That, see, auto tokenizer is to call the tokenizer that is required for this particular model, right? And here also I've given the HF_token. Automatically that tokenizer will got called, right? Then we are using auto model for casual LM. And here also you'll be able to see that we are using model ID, quantization config with respect to the BNB configuration. The device map will be equal to 0, which is nothing for the GPU. And here you can see that I'm going to use the HF_token. Okay. So once I execute this, you will be able to see that I am going to download all those information. See, auto model specifically to call those particular model, the model ID that I've given over here, by applying this quantization technique, and this entire process is going to happen in the GPU that my Google Colab is connected to, and over here I've given the token. So quickly you'll be able to see that the entire model will get downloaded, and now all the information will be specifically present in this particular model. Now with the help of this particular model, I will go ahead and test it now. Now see this, how I'm going to test it. I've given a quote over here, imagination is more. I've used a device CUDA is equal to 0. That basically means whatever is the GPU that is available. And then I'm going to use this same tokenizer. See, this tokenizer is basically getting used. I give the text and I get this particular information. So this input will be a vectors, right? And then what we do, we use this same model and we say dot generate with respect to this particular input. And let's say that I'm going to take a token of 20, okay, initially. Then once I get this particular output, the output will have in the form of list, like what all information is basically coming. So once we write tokenizer.decode of output 0, see, at the end of the day, we are doing sentence generation. So when we write model.generated, it is again going to create some embedding vectors, right? And that output, which is in the form of vector, will get decoded with the help of tokenizer. And then we'll get the real text. So if I execute this, you'll be able to, and it is saying skip special token. If any token is there, it will get removed. Okay. So once I execute it, you can see imagination is more than knowledge. I'm a self-taught artist born in 1985, right? So this information is basically coming based on the model that it has. Let me go ahead and execute once more. Okay. So here also you can able to see that I'm trying to execute one more time. Let's see whether I get a different output. So here you can see imagination is a more than knowledge, knowledge is limited, imagination encircles the word. So this information is given by Albert Einstein. Okay. So two information. And if you probably search in the internet, you will be able to find this quote also. Okay. So over here, one output we got where with the code completion. Here you could probably see that I'm also getting the author name. Okay. Now, this is what it is able to do it. Okay. So whatever information you probably put it over here, it will be able to get the output based on the information that you require. Now what we are going to do, I'm going to show you a fine tuning technique. Now see this. OS.environment WAN disabled. So one parameter we need to keep it as false. That was given in the documentation also. I did not still understand why this parameter was used, but once I know it, I'll let you know, because I'm going to create a lot of projects as we go ahead. Now we are going to fine tuning with the help of LoRa configuration. So for LoRa configuration, what all information I require? One is rank. Okay. So LoRa technique is something called as rank decomposition. We'll get to know. I've not still uploaded the theory video. So here we can select the rank value. Okay. So rank over here is selected as 8. Why 8? Why cannot select 16 or 64? You can select any number. But understand what exactly is rank decomposition. For that, I need to create a dedicated video, and soon I'll be coming up with this. The target modules, in this, you specifically require this K, V parameters, gate, up project, down project. So these are some of the target models that is required. As I said, guys, once I probably upload a video dedicated to LoRa configuration, you'll be able to understand. The task type, we always need to keep it as causal_LM. That basically means it is specifically used for this language modeling task. So this is one of the parameter that we need to set it up. So once I execute this, now let's go ahead and do the fine tuning. Okay. So this is my LoRa configuration. Now the data set that I'm going to specifically use is this. Okay. So let's see this data set. Okay. So I'll see this arbitrate English quotes. Okay. Okay. Let me see whether we are able to find it out or not. Arbitrate hugging face. Okay, I'll just search for hugging face. Now this is the data set. If you see this data set, you have two information. One is quote, one is authors, right? Based on this information, this is the quote and this is the author. And we'll try to fine tune with this. Let's say that my Gemma models knows some of the quotes in the internet along with the author. Okay. Now my main thing is that I'll have some more additional data set and we'll train with this specific data set and we'll then identify the author for this particular quote. Okay. We'll do something like that. We'll implement something like that. So here you can see that I am loading this particular data set from arbitrate_English quotes. And then we are taking a sample from this sample of quotes. Okay. So here we are going to execute this. And if I just execute data train of quote, right? So I will be able to see all the quotes over here. Okay. Quotes, you can also see the quotes, you can see the authors and all. So this entire is getting generated. And here you can see train split is also happening. And once this is executed, here I have my data set. So if you probably go ahead and execute it, you'll be able to see all the quotes. Okay. So the quotes, the sample of quotes that we have. There is nothing noble in this. So information as you can see. Okay. So this is my data set. Now, whenever we perform SFT, that is supervised fine tuning, right? We require some information. Okay. One function we specifically require to indicate what is my input and what is my output. Okay. So here we have used something like this, quote example quote of 0. So this is my first parameter, like 0. Okay. And then whatever information is there, this is my input and this will be my output. So quote of 0, author of 0. So that basically means quote of 0 indicates, I will show you it. This quote of 0 basically indicates each and every sentence over here. Author of 0 basically indicates this one. Okay. So this information will be my output and this will be my input, something like that. Okay. So once I format this, you'll be able to see that I'll be able to return my text. Okay. So let's consider over here. If I give any examples over here, right? So here you'll be able to see that any kind of examples. From that example, quote will be separated and author information will be separated. And then we return that particular text in the form of key value pairs in this list. Okay. Now is the time for SFT trainer. So here we use the model, we use the data of train. Data of train is what? So let's see this. Okay. So you'll be able to see what is exactly data of train. The same data of train you'll be able to see where I'll have all those information. This is my features, author, tag, input ID, and attention mask. Okay. Then we use some training arguments per device, batch 1, gradient accumulation steps 4, warm-up steps thing. I'm going to run it for maximum steps of 100. Learning rate is so much. FP16 is true. Then output directory will be this. Optimization will be this, right? PEFT config will be nothing but my LoRa configuration, and whatever formatting function I'm using, I'll be using it over here. So same formatting function, okay? So that I get the text in this particular key value pairs. So once I execute it, you'll be able to see it. So here you have your training will probably start now, okay? Once I write trainer.train. And we are going to run this for 100 steps. Now see how fast it is going to happen. The reason is that 2 billion and we are trying to convert that into 4 bits. So I think the training will quickly happen and we are taking just a sample of data. Okay. Sample of data. So here you can see 26 steps is done. 100 steps. And here you can also see that loss is decreasing, right? 0.39, 0.39, 0.2180, 2080. It's good. 0.131. So loss is keep on decreasing over here. Okay. Now this quote you will be able to see I've taken from one of the over here. Let's see. So here, so a human is like a tea bag and then my author should be Eleanor Roosevelt, right? So now once we execute this, I think we should be able to get that specific response, okay, from that particular model. So let's say 89, 91, 92, 100. It is reducing, it is increasing a bit, but again, it is in that step. So training output, global step. If you still want to reduce the loss, what you can basically do, you can increase the number of steps. Now here I have a quote, a human is like a tea bag, CUDA is equal to 0, tokenizer this, model.generate this, same thing. Now let's go ahead and execute it. I should be able to get the author name in forward. See, Eleanor is coming. A human is like a tea bag. You can't tell how strong she is until you put her in hot water. Okay. So that information you can see, you can never know how strong it is until you put it in its hot water. So see, all this information is basically coming and the author is also coming as Eleanor, right? So let's see this. I will also take one more example, something like this. Let's see whether we will be able to generate the same thing or not based on the data set that we have, because we have already doing the fine tuning. Okay. So I will something write like this. Okay. Now let's execute and see the output. And again, now every fine tuning you can specifically do it this specific way, right? I've just shown you in one example. The opposite of love is not hate, it's fear, and the opposite of fear is freedom, and the most wasted of all days. Let's see whether it is there or not. See, the opposite of love is not. Opposite of love is not, it's indifference. The opposite of art, faith, is not. Somewhat, it's almost equivalent, right? Fear, opposite of freedom, most of the wanted is. Okay, let's try some more. Okay. Oh, this looks unique. Unless and until this person is not a famous. The book is man's. So I will just go ahead and execute this. Let's see whether we'll be. And again, understand guys, we have just max new tokens as 20 because it needs to also complete this entire statement. So outside of a box, dog, a book is a man's best friend. See, man's best friend, author is Nicholas Comfort. The quote is again the most wasted days of all days in one. So you can probably see over here, right? Inside of a dog. something. All the information is great, right? So you can check it out with different examples. But again, at the end of the day, yes, fine tuning is good in this. Again, as we keep on doing more and more, we'll be able to do it. Now, all the application that we have specifically created, like text to SQL, invoice, we'll try to do it with the help of this itself. We'll also try to do the fine tuning. Now, one challenge that I probably see while you're building an LLM application, there is a dependency of many different tools. Okay. Let's say that I'm specifically using a model. Let's say I'm using OpenAI, and I also want to integrate my LLM app with external sources. It can be documents, it can be Google search API, it can be Wikipedia search API. So for all this kind of work, I really need to integrate with different APIs altogether. I need to have an environment key created everywhere. Let's say with respect to Google search API, let's say if I want to use vector embedding, I need to have a separate key stored for the vector databases like ChromaDB, Pinecone. If I want to probably integrate with Cassandra DB in data stacks, I need to have different connection points. Now, this is always a challenge when you are creating a project from scratch, because here to create this entire LLM pipeline, it will definitely take a lot of time. Along with that, you really need to manage all the configuration. Now here in this video, I'm going to talk about this amazing platform which is called as Vext, V-E-X-T. And here we will be simplifying this entire LLM ops. Along with that, we'll be building LLM pipelines without writing any code. So here you have almost every feature. If you want to probably implement application like document Q&A, vector embedding is integrated over here. If you are dependent on any external sources like Wikipedia or CIF, if you are dependent on Google search, everything is available over here. So you don't have to probably save all the configuration or create all the APIs. Just with one API, you can actually build this entire LLM pipeline and use that specific API in your chatbot, in your LLM application, anywhere that you specifically want to use. Now let us go ahead and let us see that how things will probably go ahead in this. You can also start completely for free. So I will just go ahead and log in over here. So I have already logged in. So here you can see with my email ID, I've already logged in. I'll show you step by step how you can probably perform all these things, right? Please make sure that you watch this video till the end. An amazing platform altogether. At the end of the day, I should be able to explain you and teach you many more things as we go ahead, right? So quickly, let's say I will go ahead and log in. So once it is logged in, and then we will go ahead and see to it. Let's see, I will go ahead and log in this way. So once we log in over here, so here you can see that you'll be able to see a dashboard. Okay, once you probably log in. Now, after you log in, all you have to do is that go and towards this AI project section. Okay, if you have not logged in, you have to sign up in this specific platform. Now, what I will do is that I will go ahead and create a AI project. So let me go ahead and create an AI project, and I will name this AI project to something else. Let's say I will write document Q&A, something I can write up to you. Okay, so whatever application, let's say I will say RAG system, right? So I'm actually trying to create this. I will enable this. Also make sure that you enable this. Then only your application will probably get started. Now in this entire pipeline, initially you will be able to see two important sections. One is query and one is output. Okay. So query basically means an event that starts the flow. Now this will be super important, guys, because a person who does not know much coding can also probably use this and create its own application, right? Entire LLM application with LLM ops, right? And you can also build the entire pipeline. Very simple. You don't even require a developer over here. Now here you have query, here you have output. Output basically means whatever is the final response that you will probably get. Now in between this, there is a plus sign over here. If I click on the plus sign, I have all these options, right? So let me zoom in so that you will be able to see to it. Okay, so over here you will be able to see, once I click on plus in, here you have an option to add an action. So first you can add a generate response. Generate response basically means a response from a specific LLM model. You can also add data sets. Let's say you want to implement a document Q&A or RAG system over here. Then you can add your own data set. Along with that, you also have an option where you can execute a function like this or smart function. Now, what is this exactly smart function? I will go ahead and explain you. Okay. Now, let me do one thing. Let me first of all add this search data set. Let's say that I have some multiple PDF file. I want to probably create a document Q&A, or it can be a retrieval augmentation generation, right? That kind of RAG system we want to create. So for this, I will go ahead and add a data set over here. Let's go ahead and create a data set. Let's say this data set, I will say these are nothing but research papers. Okay, so I will go ahead and create this research paper. Now inside this research paper, what I will do, I will go ahead and add the data set itself, right? So over here, you will be seeing, you'll be having multiple options. You can upload a plain text, you can upload a file, you can upload a page crawler, you can even use Google Drive, any file that is available in the Google Drive, that also you can add in Notion, in Confluence. So still many more options are probably coming up. As I said, for people who is not much familiar with respect to coding in LLM, they can specifically use this. Now let me go ahead and let me upload a file. Now over here, I'll click on upload a file, and then I will go ahead and upload one file over here. Let's say this is one of the research paper. We'll try to see what this research paper is all about, and I'll click on upload. Okay, so this one PDF has got uploaded. This is one of the research paper on PEFT. PEFT basically means the LoRa and QLORA configuration, the fine tuning specifically that we use in LLM models, right? So that research paper we have added. So I will go ahead and click on add resource. Okay, now as soon as I click on add source, you will be able to see that this PDF file will get uploaded over here. Let me see that. Okay, let me say that I have more files to be added over here. So I will go ahead and click on add source, and let me go ahead and upload one more file. So now there is one more research paper that is available over here. So I'll write attention. Attention is all you need. Okay, so I will go ahead and click it over here. So this is another research paper that was available. Attention is all you need. That is something related to transformers. So I will also go ahead and upload this particular file. Okay, so as soon as I upload it, you will be seeing that I have added the source. So inside this particular data set, that is research paper, I have this two PDF files, okay, the research papers itself. And I can have any number of research papers, because people will again say, hey Krish, can we just only add one, or we can add any number? You can add any number, but the maximum PDF size should be 5 MB. Okay, so this is there. I've added it. Now let me go back to my project. Now inside my project, the RAG system that I had actually created, right now I just have this two flows, right? In my LLM pipeline. Now I'll go ahead and add something called a search data set. So as soon as I add this search data set, you will be able to see that it will give me an option to select the data set, right? Whatever I have uploaded. So over there, you'll be able to see that I have my data set called as research paper. So I'll add it over here. Okay. Now you can see both this specific file has got added, right? Now, once this is getting added, there is in the right corner, right? You will be able to see there is a button in the right corner, which is called as save. I will go ahead and click on save. Okay. So once I click on save, that basically means this ingestion, the data ingestion that is specifically required, is now available inside this search data set. Okay. So over here, you'll be able to see this search data set, because I want to implement a RAG system, or it can be a document Q&A. I can probably ask any question. It should be able to give me the response. So inside this particular data has got added. But internally, what this system is doing, it is already creating that entire embeddings that is specifically required. Internally, if it is requiring any vector store, it is creating all those things. Okay. Now this is done. So this in turn is my data ingestion step. Now coming to the next step. Here, let me go ahead and generate a response, because here what I will do, I'll add an LLM model. Okay. Now, any question that I specifically ask to my data set, it should be able to give me the answer and summarize that answer using this LLM, whatever LLM I'm selecting over here. So generate a response, you basically select over here, and you have multiple options of selecting different models. Now see, it is also providing all these models. Azure OpenAI GPT 3.5, Azure OpenAI GPT 4, Anthropic Cloud Instant, Anthropic Cloud, Google Gemini Pro Beta, and in the future, so many different models are coming, like Llama 2 and all are also coming. Okay, and the best thing about this model is that they have hosted this particular model in their cloud, and they are providing it as a service to you. Now let's go ahead and select any one. So let's say I will go ahead and select Azure OpenAI GPT 4. Okay, now here you can see it is showing the next field as purpose. So in short, here you'll write your prompt, like how you want this particular model to behave. So I'll say you are a helpful assistant who please answer the questions based on the context. Okay. So this is what is my prompt. I've written it over here. Now there is also one more option which is called as behavior. Any additional thing that you really need to give on top of that particular prompt, you can give it over here. Let's say over here, one example is the behavior of this AI application. Be as specific as possible, be very helpful and assist user, something, any additional prompt that you really want to write. Right now I'm not giving anything. So let me quickly, or let me just give one. Okay. So that I'll say be helpful as much as possible. Okay. So this is done. So now what I will do, I will go ahead and save this. Okay. So on the bottom right corner, you'll be able to see a save button. So I'm going to save this. Now this is my entire LLM application, right? So any query that it'll go and probably search in this particular data set, and then it'll give me a response. Now quickly to check this, whether it is working absolutely fine or not, here there is an option of playground. Okay. Now in this playground, I will go ahead and ask all my questions that I want. See, 2 research paper that I had added. I will talk about both those research paper. One is PFT for one research paper was something for this parameter efficient transfer learning, and one research paper was attention is all you need. So here I will go ahead and ask the question, what is parameter efficient transfer learning? Okay. So I will go ahead and click on send. Now let's see whether we'll be able to see the response or not. So in short, what is happening now? Any query that I'm giving, first of all, it will go and search from this particular data set, which is already in the vector embedding format. And then whatever information is going to come based on the prompt, it is going to get summarized by this LLM model. And finally, we are going to see the output result. And understand one thing is that based on the context, whatever context it is available or whatever context we are able to retrieve from this particular data set, that response we will specifically get it. Okay. Till we get the response, I will just go ahead and search for some more questions over here. Okay. Let's see. Experiments. Let's say I will go ahead and ask instantiation for the transformer network. Now here you can see I've got the response. Parameter efficient transfer learning refers to the method used in machine learning and specifically natural language processing that allows for the transfer of knowledge. And here you are specifically getting your entire answer. Okay, let me just go ahead and let me talk about what is attention is all you need. Okay, so because that research paper also I have added. Okay. Please summarize. Okay. So I've given this and here I will go ahead and click on send. Now the best thing is that the same functionality I can integrate with any chat bots that I specifically want. Let's say in Telegram channel, in WhatsApp channel, in any channel as such. That option also I'll show. Now again, I've got it. So attention is all you need is a semi-research paper by Ashish Vashwani and colleagues. So perfectly we are able to get it. Okay. So any Q&A with respect to the data set, you will be able to get it. Now here you see that you did not have to write much line of code, right? And it was very simple, just by drag and drop, adding the feature, adding the data set, everything you are able to do it. Okay. Now let me go ahead and add one more function. Let's say that I'm going to add a smart function. Okay. See, execute a function basically means here you will get some options to write, to probably do basic maths, Wikipedia search, Google search, archive. Like let's say you want to ask queries from this particular, archive where all the research papers are uploaded. You can probably use this. Okay. So you can specifically use any of this activation function. One more, if you want to go ahead with, is something called as smart function. Now inside this smart function, you can add multiple functions altogether. So let's say that I want to do a Google search. So I will say over here, you can see in the description, it allows users to perform searches on the Google. Let's say I want to also go ahead and use archive. If I want to also go ahead and use Wikipedia, I can actually use over here. So let's say that I'm adding all this smart function over here. And for right now, what I will do is that from my first flow, I will remove this search data set because I don't want to use data set, right? So let's say I'm using in this particular way. Now let me go ahead and quickly search in this playground. So if I go ahead and write, what is machine learning? Okay. So if I press enter, you'll be able to see that now it is going to do the Google search and it is going to give me the specific answer. Okay. So, and for the first time, once you set it, for the first request, it will take some time, but from the upcoming request, it will become very smooth. So here you can see machine learning is a branch of artificial intelligence and all. So let's say I will go ahead and write who is Krish Nayak. So here, if I go ahead and click on send, here also you can probably see that if it is using the right API, Google Search API, it should be able to give me the answer about myself. Okay, so Krish Nayak is a YouTuber and data scientist known for his educational content on machine learning. So all the answers are perfectly coming up, right? Now, this is what is the most amazing thing about this. But again, that question will come. Krish, what is the use of all these things? You know, you are saying that we can do all these things in a specific platform, but how to probably do this in the coding? Because I want to use this entire functionality implement in my chatbot. Okay. So let me talk about that. Okay. So if you go ahead and click on the output, so here is what is the most important thing. Here you'll be able to see that you get the HTTP request and you can also get the entire post request, right? So once you probably get this post request, inside this post request, you just need to set the API key. And then by using whatever payload, like whatever is the question, you need to include it over here. And then by hitting this particular URL and this channel token, you can probably see this should be unique, some unique name. Okay. So here I will show you. Okay. I'll give you the code also how you can actually hit the post request with the help of Python programming language. Now what I will do, first of all, I require an API key. Right. So if in order to create an API key, what I will do, I will go ahead and click over here. And here you can see I will go ahead and click create an API key. So let's say I go ahead and write test. This is my AI project or the rack system. And this will be my API key. Okay. Please make sure that you save the API key. So I'll copy this API key. I'll paste it over here. Okay. So this is my API key. Now what I will do, I will go back to my AI project. Okay. I'll go back to my AI project. I will take the code, the post request. Okay. Now see this entire pipeline. I just require one API and with that I can do a post, I can do a get and all the functionality I'll do. I don't have to even worry about the vector embeddings. I don't have to worry about the APIs of search, Google search or RSave or Wikipedia. I don't have to worry about it. All I'll be worried about this specific API itself, right? So what I will do, the same curl post request that you'll be seeing, I have written this in a normal Python code. Okay. So here is the entire Python code. Here you can see, this is my API key. So API key, I'll just update it. So this is my older API key that I had actually tried it out, but don't use this API key. It will be of no use because I'll be deleting it. And then here I will write the query. What is machine learning? Then I'll set the headers of content type of application JSON. The same thing. See over here, content type is application JSON. API key, I need to set it up and then the payload which will have my query. Okay. So I will go over here. So API key, I have set it to API key, whatever API key is there. My query is what is machine learning. And this is my entire data payload. All I did, I took that curl post, I just searched in the chat GPT and it gave me this entire code. Okay. Then this is my URL. And instead of that catch token, I'm writing Krishnaik06, a unique value. You can put it anything over here. And then I'm doing request.post with this URL, with this JSON data and headers is equal to headers. Okay. And I'm printing the response.txt. Again, see the code. It is very simple. I'm setting the API key. This is my query. This is my headers. This is my data. I'm just setting it up, whatever is the post request. And now let me go ahead and execute it. Now, if I go ahead and execute it, the best thing will be that, see, I will write Python test.py. I've asked the question, what is machine learning? Okay. Now here you'll be able to see that I will be getting that entire, okay, text. It shows unauthorized. Okay. Let's see what is the error. Okay. I have not saved this one. That's okay. No worries. I had not saved it. So that is the reason. Now I will be able to see the response. Cannot match app with endpoint. Perfect. So still this is not matching because I had already tried it out previously. So let me do one thing. Let me copy this again and then you'll be able to see it. Okay. So I will copy this entire URL and the channel token will be almost same. Okay. So from catch, I'm pasting it over here. So I'll remove this. I think it is $catch. This catch should get removed and this will be my $channel token. Perfect. Now let's see. Okay. Now it should run. What is machine learning? And now I think I should be able to get the answer. Okay. So let's wait for the first time. It will take time, but after that, I think it will work absolutely fine. So this is done. But at the end of the day, you can see that it's a simple Python code, a post Python code. And how you really want to use it from the front end point of view, it is up to you. You can specifically use it. But this is my endpoint. This is called as an endpoint. This is my API key. The API key is basically getting appended over here. So now here you can see that I'm getting the response. Machine learning is a subfield of artificial intelligence that involves the creation of algorithms, so and so, everything is there. Now this simple post, I can include it in any API that I specifically want. Okay, that is the most amazing thing. So coding wise, you can now see you don't have much dependency. Now, one more thing that I really want to show, there is something called as app directory. You can also connect with Google Drive, Confluence, Zapier, Slack, Teams. So all these things are coming soon. Later on, you can also work directly with LLMs and bring your own LLM to the platform. Here you have AWS SageMaker, Bedrock, Hugging Face. It is also having this entire support. So guys, in this video, we are going to discuss about how we can fine tune our own LLM models with our own custom data. For this purpose, we will be specifically using this platform, which is called as Gradient.ai. Now, Gradient actually provides you a lot of LLM models. On top of that, you can probably do a lot of fine tuning with your own custom data set. Custom data sets can just be formatted in a specific way to give it, and later on, the fine tuning can really happen in a quicker way. So probably when I will be doing the fine tuning, it hardly takes 7 to 8 minutes. This is the demo that I really want to show you in this specific video. By doing this, you will get an idea. If you have a custom data set and you want to also create your own custom LLM model, you can definitely do it with the help of Gradient.ai. Now let's understand what does Gradient.ai provides you. It is a one platform, unlimited AI. It not only does the fine tuning, it helps you to develop it, deploy it, and even for the inferencing part. So over here, you can create your own private LLMs, your own models, fully unlocked models, right? And you can build with any languages. It provides you 3 SDK, I think JavaScript, Python, and Java. So that is also provided. We will be specifically using Python SDK. We will be using Google Colab, and we will be fine tuning our own model. So it is the only AI platform that allows you to combine industry expert AI with your private data. And here is all the other information that you can see, that it also provides accelerate AI transformation, deploy AI to solve mission critical problem, 10 into faster with Gradient's AI cloud platform. We handle the infrastructure for you. So it is an amazing platform altogether, where you can not only build your model, even you can inference it, you can even fine tune it. So in order to go ahead with, first of all, you need to go ahead and sign up. So for sign up, you can probably put your entire details. I've already signed up. So I'm going to probably do the login over here. As soon as I do this logging, it will ask you to create a new workspace. So this is the first important step that you have to do. So for creating a new workspace, you just need to create, just click on this particular button, create a new workspace. You can give your own workspace name and just submit it. Once you submit it, like in this case, I've created a test workspace. You need to know this specific ID, because this ID is nothing but it is the workspace ID. So I will copy this workspace ID so that I will be using it in my coding when I probably do it in the Google Colab. The next thing that is specifically required, you need to click on the access tokens, right? One is the workspace ID and the other one is the access token. Again, to generate the access token, I have already generated it. I have kept it in my coding environment. All you need to do is that just click on generate new access token, and you have to just put your password, submit it, and it will give you the access token. There you just need to do the copy over there. So what I will do, I will go ahead and give my password as soon as I do this. So here you can probably see that you get your secret access token. You can copy it over here. One amazing thing about Gradient AI is that it provides you all the necessary documentation over here. You can just go and refer the documentation. It provides you the entire code that is actually required with respect to Python SDK. And trust me guys, just with a minimal lines of code, you can probably fine tune your entire model in an easier way, right? So if you probably go to the guides, here you have something called as Python SDK example. So with respect to Python SDK, you can probably see this is the code for fine tuning. I will copy the same code and I'll probably run it. But here I'm going to make some changes with respect to my data set. Along with that, you can also go ahead and see the entire documentation, whatever things you specifically require. The integration it specifically provides for LangChain, Llama Index, MongoDB, Haystack, so whatever things is specifically required. MongoDB and all, you can probably do the vector data. You can create it as a vector database and probably store all the vectors over there. Now let me quickly log in again. So once I log in, if you probably go to the workspace, okay, so this is the workspace that I have actually created, okay. Now inside this workspace, you can see all these are the models that I have already created for the fine tuning purpose. If you probably go ahead and click on fine tuning, and if you see, if I just go ahead and select or create fine tuning over here, it provides you 3 base models, okay. One is the Bloom 560. One is Llama 2 7B chat, one is Nos Hermes 2. Okay, so these are different models, LLM models. You can use any one of them for the fine tuning purpose. Now in our example, what I'm actually going to do is that I'm going to use this specific thing, and then what will happen is that with the help of Python SDK, I'm going to do the entire fine tuning process. Here, then I will be able to see my fine tuning job also as I go ahead. Okay, so here I have opened my Google Colab. Let's go ahead step by step and let's see that how you can probably fine tune your LLM model. So let me first of all make this spelling mistake correctly. Okay. Now the first step is that we will go ahead and install Gradient AI. So for this, I will be using pip install Gradient AI upgrade. So once I execute this over here, you will be able to see that the installation will start taking place. Now it shows that requirement is already satisfied. Now, the next thing is that the 2 important information, as I said, one is the gradient workspace ID. I've already shown you from where you can probably get your workspace ID, right? Initially in the workspace, when we were probably checking it out, that particular ID, I had copied it over here and I pasted it over here. And the next ID that I really need to set it is my access token, gradient access token. So I will set up the environment by using import OS. And then I'm going to probably use os.environment gradient workspace ID with my workspace ID itself. So this is the ID which you will again get it from the gradient itself once you log in. And the second thing is about the gradient access token. So here also I have pasted the access token. So let me just go ahead and execute it, and I have set up this environment variable. One is the gradient workspace ID and gradient access token. Now is the most important thing. This is the code of the entire fine tuning. So let me go ahead step by step and see like how the fine tuning is basically done. So first of all, we will go ahead and import from Gradient AI, import gradient, right? So this gradient will be responsible in fine tuning in even calling the base model. Now I've created a function definition main. Now this is the function. Initially I have initialized gradient. Okay. Inside this gradient, you have a method which is called as get base model. And here the first parameter is something called as base model slug. That basically means what model you are specifically calling. And I have already shown you in the fine tuning, right? If you probably go ahead and create fine tuning through the UI, you have these 3 models that is there. Bloom 560, Llama 2 7B chat, Nos Hermes 2. So in this case, I'm going to specifically use Nos Hermes 2. Okay. Now Nos Hermes 2, I'm going to do it. See, you can also do it with the help of UI, but I really want to show you with the help of coding by using Python SDK. So here is the same model. I have pasted it over here, right? So this specific model over here is my LLM model that I'm going to fine tune. On top of it, I'm going to fine tune it with my own custom data. Now, once we created this base model, so this line basically gets you the base model over here. Now this model will be responsible, and we will try to create a model adapter, right? The reason we are creating a model adapter, because this will be specifically my model. Let's say this is like Krish model over here. And this model, the reason we are creating as a model adapter, because in further we will be doing fine tuning for this particular model itself. So the first step is basically to create an adapter on front of it, right? And the name of that particular model will be Krish model itself. So this is the second line of the code that we have executed. Now here we have created the model adapter with the ID new model adapter.id. So we will be getting the ID itself. Now is the most important step. I will try to go ahead and create a query. So this is my sample query. The instruction, see, I've given some kind of format. The instruction is who is Krish Naik. So this is the question. And usually what happens is that in gradient, you really need to use a specific format in creating your custom data. And for that, you can refer this Python SDK. Here you have some tips and tricks. It will talk about like how you can probably create your entire data itself, right? With custom data. So you can check it out, this specific thing. And with respect to that, you'll get an idea like how your data set should be created in a form, right? So some format should be there. So let's say if I ask any query, right, for a base model, something like this, I've given this tree hash, and then the instruction, this is the question, who is Krishna? And then we are closing it with to end line. Okay. And then we will be seeing the response. So response over here is kept as blank because this response is going to come from this specific new model adapter. Okay. Which has the base model Nos Hormuz. Okay. Now we will be printing this sample query. So already it will be just going and printing this with all this information like instruction and response. Now this model adapter, when I say dot complete, okay, so dot complete is a method over here. The first parameter I will be giving my query, that is my sample query. The max generated token I will be giving 100. So it is going to probably take 100 max token in the form of output. And then we are going to use dot generated output. So this is one of the attribute that is present inside this dot complete method. Okay, so after this complete method, we will be getting the generated output. As soon as we get the generated output, that basically means whatever questions I have asked over here, who is Krishna, I'm going to get the output over here itself, right? So generated before fine tuning. Now here is my output that I'll be getting, and understand I have not started my fine tuning. So that is the reason I have written a comment over here before fine tuning. Now before fine tuning, if I ask who is Krishna, obviously this model will not know unless and until I'm very much popular. Okay, I'm not that much popular. So it will just say that if it has heard somewhere Krishna, it will give some information. Now what I will do, I will go ahead and create my own sample data, okay, regarding Krishna. Because obviously over here in before fine tuning, if I probably execute it, I will not be able to get the output, the right output. Now this will basically be my custom data. So here you can see that the first question that I've asked, the first sample, that first input data that I've created, which will be used for training, is that who is Krishna? Then over here, the response I have written as Krishna is a popular mentor and a YouTuber who uploads video on data science and LLM, and his channel in his channel Krishna. So this is one of the input and the output that I have given. The similarly second input I will again create who is this person named Krishna. Now I'm giving in a different format of text like question and answer, right? And again the response I have written Krishna likes data science and AI, make videos in YouTube, and he's also a mentor, right? Something like this. Then instruction again, what do you know about Krishna? Okay, so again I have created one more response. Krishna is a popular creator who specializes in the field of data science, and his channel name is Krishna. Okay, and again one more input. Like this I can create a lot of inputs related to a single context. Now suppose if I have 100 of context, I may probably create this kind of inputs. And at the end of the day, if in a real world scenario, in an end-to-end project, if you see, this all information will be coming from some kind of databases. It can be a MongoDB database, it can be a SQL database and all, right? So this will be my sample of data. It's just like more like a key value pair, you know, a list of key value pairs. Now this is done. Now what I'm going to define after this, my input is done. My model before fine tuning is done. Now I need to do the fine tuning. So for performing the fine tuning, I need to have number of epochs, one parameter. I will initialize count is equal to 0. Now I'm saying while count is less than number of epochs, and then I will start my fine tuning over here. So fine tuning count plus 1, then I will say new model adapter dot fine tune is one method where I am giving my samples. Okay, so samples over here, this all samples I'll be giving it over here for the fine tuning purpose. So in short, I'm using a method which is called as dot fine tune, and we are specifically giving the samples over here. And then we are incrementing the count so that the epochs keeps on increasing. So first iteration 1, iteration 2, iteration 3, and then this entire fine tuning will happen. Okay. Now after this, I am again writing this comment after fine tuning, and I will execute the same method right over here by giving the same sample query, who is Krishna, right? And over here the same thing is there. I will get the generated output. I am going to display the generated output, and after doing this, I am deleting my adapter because I will not require it afterwards. If I wanted to use it further, I can keep it like that. Otherwise, I can just go ahead and delete it. And here also I'm closing the gradient. And this is where I am starting my main. So this is in short, what we are doing is that before fine tuning, I really want to see the response. I created my sample data over here. And then again, I did the fine tuning with respect to number of epochs and all. And now let's go ahead and execute it. So once I probably start executing it, you can probably see it will start. It may take hardly a couple of minutes since I've just done 3 iteration. Okay, so here created model adapter with this particular ID. The instruction is who is Krishna, so it is waiting for the response. Let's see over here whether it has been created or not. Model testing. Let's see, fine tuning. So here also it will, as soon as the fine tuning will happen, here the model will get created and it will get deleted. Okay, it will get deleted. So here the response it is getting that Krishna is a well-known Indian actor who has prepared in various films and television shows. Is best known for his Raj in the popular. I've never worked in any industry, guys. Okay, so it is saying I'm an Indian actor. I'm not an actor altogether. Kyunki saas bhi kabhi bahu thi. Okay, so this is a very famous serial in India. Okay, I have never acted over there. I don't know whom it is considered. Okay, that's also said that I've worked in Dil Chahta Hai, Kal Ho Na Ho. Nice. So now I am doing the fine tuning. So this is the response that I've got generated before fine tuning. And now after fine tuning, I have given the right kind of data with respect to input and the response. The third iteration is getting over. See how fast it is happening in the cloud platform, gradient cloud platform. That is quite amazing, right? And this is super, super nice. At the end of the day, you'll be able to see this, right? Beautiful, right? We are already in the third iteration. And now here I'm getting my output generated after fine tuning. Krish is a popular YouTuber and data scientist, known for his data science and Python tutorials on his YouTube channel, Krish Naik. Now see, just with this 3 sentence or 4 sentence, how well it has done the fine tuning. Now just imagine the power, guys, right? The entire fine tuning is happening in the gradient cloud itself, right? If I probably give this kind of data and just increase the number of epochs and train it, how beautifully within 5 to 7 minutes you can actually train it. And hardly, just to put my input data, it hardly took very less time, right? So this is one amazing application. This is how you can probably do the fine tuning. One task I really want to give it to you. Okay, let's reload this. I think you'll be able to see my fine-tuned model also. Let's see the model. Okay, I've already deleted it, I think. Yeah, I've deleted it. So that is the reason you're not able to see it over here. If I had not deleted that, you could also see the models over here, right? So model testing, see model is also not here, right? Otherwise, you could also see it, put it over here and you can ask any question you want, right? This is quite amazing. So at the end of the day, if you don't want to delete it, just don't delete it and keep it like this. So I hope you like this particular video. I hope you have understood how you can fine tune our amazing LLM models with the help of Gradient AI Cloud, which is quite amazing. You should definitely use it. Try to use it and try to see whether you're able to do this or not. But just by seeing the code and all, I think it is quite easy, quite amazing. Again, yes, this was it from my side. I hope you like this particular video. I'll see you all in the next video. Have a great day. Thank you and all. Take care. Bye-bye.